Okay. Is it a hump or a drop? What do you say? You've got to twist your words in every which way, because the model will always dictate what you do. Everybody knows that you've got the model affliction blues. Is it a straight line, or does it curve? Some people don't clamp it, but that is absurd. We all know that the model dictates what you do. And everybody knows that you've got the model affliction blues. Model affliction, it's your addiction. Model affliction, it brings you so much pain. It's your ball and chain. Conflating curvature with elevation change. Just got your local distance just out of range. That oblique is gonna dictate everything that you do. And everybody knows that you've got the model affliction blues. Model affliction, it's your addiction. Model affliction, it brings you so much pain, and it's your ball and chain. It's your decision defending the model position. You just don't know the geometric proposition. That old ball will always be illogical to you. That's why perpendicularity is a puzzle to you. Model affliction, it's your addiction. That old model affliction, it brings you so much pain. It's your ball and chain. And everybody knows that you've got the model affliction blues. Works really good with this guitar. Is it a hump or a drop? What do you say? You got to twist your words in every which way. We all know that the model dictates what you do. Well, we know you got it, the model affliction. Model affliction. Model affliction. Model affliction. the model affliction blue.
And we are live. Welcome everyone. It is it's Monday. What have I built this one as? That's a model affliction Monday, isn't it? We've if you were just before this one, was one of those weird flat earth guys who said he came on here on Friday, free for all Fridays, and he said that he'd measured a triangle, just the one, a triangle, with more than 180 degrees. Now, despite being impossible, it's a very good claim. Not done by too many. I don't know whether you heard the intro as well, because we had there's another guy called PhD Tony, and he was talking about triangles with 180-degree angles, which is even more fantastic. But when it's incomprehensible, really. We're going to be going over that. The way that you can say, you know, a triangle with three 180-degree angles, and it's that unbelievable, it's that absurd that you can't even comprehend it. So therefore it means nothing. Your brain just gets shut down whenever you hear something so ridiculous. I'm thinking it's some sort of a way that magic is performed. The ability of people to be able to perform magic on each other's is through this absurdity. You make it so incomprehensible. Well, thank you very much, Gods. Thank you very much. And Gods, give us some members. So click your thingy and you get a free membership. Thank you, Godzilla. Yeah, so we've got ridiculous claims, and coming up there is, because we've heard that the dogmaticians, the one that he presented, apparently presented a Betty's aporia, a proof of aporia over at Blue Marbles, and Betty just handed it to the Blue Marble scientist. We're going over the Betty's side rule. This is, I don't know whether he came up with this. He definitely talked about it here. You can see there in the chat. I don't know whether he's told the Blue Marble scientists about this, or whether this is a generally accepted rule for the Blue Marble scientists. We don't particularly do this. I'd like applaud anybody for anything, really. I mean, I have said quite a few times I applaud certain things that certain people do. Anytime Blue Marble Science and the Blue Marble scientists actually go live, I do applaud them for getting together and talking with each other. But Betty's side rule is that you should never applaud the other side. I think that's a bit unfair, really, because what you always have to do, it makes people choose sides. The idea that there are sides to reality is unfathomable for me. I just can't understand it. I can't think why people would have a side as far as understanding reality is concerned. Just seems ridiculous. So the rebuttal to the side rule, I would say, is don't choose sides. There's no need for you to put yourself on a side or put other people on different sides, or even to imagine that there are sides to any of this. But hey, that's what we're dealing with. Modern day 2023. I'm progressing. We're gonna have to be aware of the snowflake rules and the side rules. Betty, it was Betty that said that there are sides, and the sides are the blue marble scientists and the on the level. Well, I consider this place as a place where we go to the depths of the advanced simplicity, just breaking things down to make them as simple as possible. We are going to be going into the logic side, and also the sophistry involved with what we call the non-debate arena. Basically, it's built upon the idea of this side thing. If you can have people on different sides, then you can always just wait for the other side to say something and then say not that. Just rebut it with a quite a simple not that. Which I think at this sort of time, 2023, it's about time we rise above this ridiculous thing. And also shining a light on these things is normally the best way to let people know, because sometimes you don't see it. Sometimes there can be something right in front of your face, like with you talk about these magic tricks. There can be things right in front of you that you don't see, that need to be pointed out. Now, I've been testing it myself as to what people can see, and how blatant you have to make this to point certain things out to people. So I'm going to go over tonight. I think I haven't really got much planned other than letting people know that the failed the vertical and horizontal being perpendicular. Buster sung it in the beginning. Perpendicularity is a puzzle to you. Well, that idea of vertical and horizontal being perpendicular is the problem, because I've been told today by a sophist that there can be only one vertical perpendicular to a horizontal. I know, it's ridiculous, right? But somebody told me that today. We're going to have to obviously, this is the flat earth math triggering, because the 1 degree every 69 miles was an initial drawing that I did, showing a 1 degree change over 69 miles. 69 miles being a straight line and two angles measured at either end. So, pretty simple to understand, but I think Betty wants to come and have a discussion about it, about how ridiculous it is that flat earth math couldn't understand it. And I think it's something to do with the fact that triangles having 180 degrees is the basics of trigonometry, yet the contradiction lies where certain people like flat earth math thinks triangles have more than 180 degrees. It's a bit hard to live with both of those facts within the dogmatic globe model. Is that a hot mic, Kev? Do you want to come in? Let me get this video. Right now, I'm going to go over a video, but this video will be only have to go out on the YouTube. So if you want to actually come in and watch this video, you'll have to come into the Discord, because I know for a fact that the person that this video is in this video will copyright strike. That's the sort of person he is. And but we're talking here about the argument that's presented. It's about a 20-odd minute video. Let me get it for you guys in the YouTube. Wait a minute, what's going on? See. There you go. Might I be able to show you a screen or two whenever we pause it? So this is obviously a video, right? Are you guys ready? Can you guys see? You're in?
Yep.
Okay.
Yes.
So this is basically we had a little bit of a run-in, let's say, with this dude, and he tends to copyright strike everything. In fact, he nearly got my channel shut down, but unfortunately it didn't. Fortunately, but he's put multiple copyright strikes out, and he does it for whatever reasons. But as you can see, he's going over a video from somebody else, but this is just the way it works. Oh, actually, we've got Charles in here. We've got the angle measurer, triangle measurer. Were you impressed with that, Charles? In the video, you were the first person to claim to have actually measured a triangle with more than 180 degrees. So you know that we know that triangles have 180 degrees, right? And you know that we know about planes on a sphere as well.
I'm very, very sorry. I am so Discord clueless, but I'm also YouTube watch page muting clueless. So I was hearing you on the watch page, and then I was switching over to Discord because you were saying, hey, we're going to watch this video. So I'm like, all right, let me switch over to Discord. And then I started to talk over top of yourself, and I'm like, why are you talking over top of yourself? And I forgot that I YouTube. Anyway, yeah. So I don't want to interrupt your show. I just want to say, 12 words. Planar triangles add up to 180. There's no contradiction there. All of Euclid, 100% is correct. Planar triangles add up to 180. All right. So if you have three points and you have a plane and you have all the lines are in the plane, adds up to 180. If you have a spherical triangle, however, the angles can add up to more than 180. Actually, they have to add up to more than 180. And that's what I was talking about, what I measured. All right. And I'm actually working on a video, but I'll let you go. I don't want to interrupt your show. I'm happy to join on Fridays. So
okay. Well, it's Model Affliction Monday, right? And
Model Affliction. Sure.
The fact that you claim that you've measured a triangle with more than 180 degrees. That's
spherical.
No, you didn't say spherical. See, that's the problem. You imagine that you've measured a triangle with more than 180 degrees. The fact that you put another word in front of it means nothing, because you know that it's not a triangle that you've measured. If you indeed have ever actually measured? Like, what was the device that you used for your angle measurements?
I just look. Well, it was azimuthal, so I took the 3 locations, and it was Brian. It was Brian's logic. I think I said Brian Leakey by accident. It was Brian's logic. There's a video called the American, I don't know, American triangle of globe destruction or something. And so I just took the points that Brian's logic had picked. One's in Seattle, one's in Lompoc near Los Angeles, and one is in New York City. And I just took the azimuths. So, standing in New York City, shoot an azimuth to Seattle, also shoot an azimuth to Lompoc, near LA. And those were the angles. I did the whole thing with just looking at the angles on the map.
So you didn't actually measure an angle.
I was not actually out in the field.
Okay.
But it was interesting because in his video,
It's
he did not measure the
you
angle.
choose the word for measure. You measured a triangle with more than 180 degrees. They were your words.
Yeah, this is true.
So you didn't.
The word
actually
measure
it.
can.
Yeah.
The word measure can frequently means compute. There are very few. There are very few applications.
Rules of the law of identity here. Measurement is something that is done physically, right? It's a measurement.
No,
not a calculation. There's a difference, isn't there, between a measurement and a calculation?
Well, not necessarily. Even if you step on a bathroom scale, any bathroom scale that's made in the last, say, 20 years doesn't have springs in it. It has strain gauges, which means it's a little piece of metal where when it's under strain, the resistance in that metal changes. And so the computer in the mind of the scale is interpreting that strain gauge, the strain change, to a measurement in pounds or kilograms or whatever. So literally your bathroom scale is doing a computation based on a strain gauge. It's not an actual direct measurement. It's a computation. So that's most measurements are computations.
You are giving wrong example. Sorry, there is a physical change in that bathroom scale. So that would be measurement of this changing of quality of this metal or whatever.
Right, of resistance, electrical.
Weight, right?
No, it's what the scale is measuring is the change in resistance of a piece of metal, electrical resistance.
Right. Yes,
that it is translating that to pounds or kilograms based on a table.
So you have still
computing.
have you have still physical phenomenon or electrical phenomenon.
Yeah,
whatever. Yes, so
it's still a computation. The digits that are on the screen are still being computed.
Yes,
by some formula.
After noticing, let's say, change in this metal or whatever. So it has to notice this change of something. Otherwise, it wouldn't compute anything.
Right, but it still is computing.
Right. Yes. So that's
ultimately it is computing.
No, it is measurement of something.
We can go in circles. Anyway, I get your point, Paper. That it's measuring a physical change, and then it is translating that physical change into pounds or kilograms, but it's done through a formula.
The same thing is with triangles. When you can measure angle, and then you can compute, of course, whatever you want, but still it is able to be measured. This is not about physical measurements per se, but about ability to do it.
Right. But I mean,
you are not able. Pardon. You are not able to measure spherical triangles angles. You are not physically able to do that.
Right. I mean, it all depends on how strict you want to be. I mean, I think everyone has seen those signposts. Usually, it's in like a war movie where somebody makes a signpost and they say Paris, 5,000 miles in that direction. You know, like here they are in the middle of some jungle warfare or whatever, and they're like, oh, wouldn't it be nice to know that Paris was 5,000 miles in that direction? And then, you know, New York City is, 12,000 miles in the other direction. We've all seen those signposts, right? I mean, they're done as a joke, right? But if you could imagine such a signpost, but it had a very specific direction. You know, if you're standing in Seattle, what direction is New York City? Exactly. If you're standing in Seattle, what direction is Los Angeles? Exactly. That's what I'm talking about. So if you had those two directional pointers,
lines? Yeah.
if you have those two, and I would call them azimuths, if you knew the azimuth to one location and the azimuth to a third location, you could compute the angle between them. And I would call that an azimuth angle.
If you had a map, you could put the point that you are at, and then you could put a line towards wherever one of your points and a line towards the other point, and then you would have what you call an angle, and you could measure that angle with a protractor.
That's what I did. I was using the maps provided by Brian's Logic.
So you did measure it with a protractor.
Well, not a protractor. I mean, I used the digital equivalent. I mean, I used the azimuths. But I did, ultimately was measuring those three angles, and they add up to more than 180.
Right. So what's the digital equivalent?
Well, like I use Keynote, and so in Keynote you could just draw a line on the screen, and you can measure the angle of that line, and then I did that twice, and just subtracted and found the actual acute angle.
You did it twice.
Well, no, I mean and I don't know if you're a Mac guy or a PC guy, but I use Keynote, so I just use the line drawing tool, and in the inspector it says what's the orientation of this line in degrees. So I drew one line, and I got the angle in degrees of one line, and I drew a second line, and I got the angle in degrees of that second line, and I just subtracted to get the angle.
You measured a single line and got an angle.
Oh, no.
It's got twice.
It's orientation. So in Keynote, are you a Mac guy or you a PC? I think you're a PC guy, aren't you?
Yeah, I'm a very simple guy.
But, a PowerPoint probably has the same thing. You can draw a line on your screen, and it will give you the orientation of that line. And that orientation is written in degrees. It's not an angle measurement. It's a direction. It's like azimuth, but it's not. Usually, I think due east is like 0 degrees, whereas with azimuth, due north is 0 degrees. So you have to do a little bit of math, either adding to or subtracting from 90 or 180 or something. But I hope you understand. I drew one line, and I got the degree orientation of that line, not an angle, but the orientation in Keynote. I did the same with the second line. It's the equivalent of drawing two azimuths.
Do you think doing? Did you do that 3 times?
Yes, for all 3 locations.
So 3 different lines that you found the orientation of 6 different lines.
Yeah, 6 different lines. Yes. Subtracted and yeah. And I think I did
the angle from that.
Yeah, it was 184 degrees total for that triangle.
Right, but that's not. That's not how the triangles are done, is it?
Because it's not a planar triangle. I'm going to make a video. I don't want to interrupt your show, okay? I just wanted to pop in because you said my name, so I popped in. I do not want to interrupt your show. I'm going to let you guys, go on with what you got going. But I just wanted to say hi, Bev. I appreciate the hospitality. But I'm working on a couple of videos, one of which is the 180 degrees. So, all right. So I'm gonna jump out. I'm just watching. I came in because I wanted to watch the video because the copyright strike. All right.
Yeah.
Okay.
Okay.
I'm going to mute.
We've got Brad, the science guy, seems to be promoting this blue marble science and these reciprocal zenith angles. It's fantastic. Okay, so we'll go over this now. What the problem that is caused between these triangles? I mean, everybody knows that triangles, when you measure it, you go from A to B, and that line is the shortest distance between A and B, and that would be measured as a straight line. But that straight line in reality becomes a problem for a dogmatic globe believer. Gets really tricky, and this is where it happens, and this is where I think we got to watch it real time. I don't know whether it was last year or whenever, a bit of time ago, let's say. We've been around here for a bit, and this is how you nutsack yourself based around the straight line in reality. So triangles from A to B and B to C, that makes a triangle. Now, the shortest distance in reality from A to B is measured as a horizontal. If it's not horizontal, then it's sloping, and therefore a longer distance because you're working on the hypotenuse. If you go horizontally, then all perpendiculars to that will be vertical. That's just mathematically in reality. But so other people have problems with that. But keeping it simple, the shortest distance from A to B is a horizontal, and all perpendiculars to horizontal are always vertical. On we go with the problems. So we'll have to keep pausing this and go over it. Here we go.
Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy.
Wait a minute. Oh, sorry. I think he's allowed to lose that title. Maybe because of this video, this sort of time. And he may have doxed himself there, but I mean, hey, who knows?
Today I'm doing a little longer video than normal, which is why I didn't release it at 7 this morning. I'm releasing it as a premiere here in the afternoon. Now, once we're done with this, I'm going to go ahead and open up Discord, and we're probably going to broadcast that as well, because I thought it would be nice to get a group of us together to kind of discuss some of these concepts and maybe go over some more videos.
See, it's a good idea for them to get together. Anybody that wants to come and get together, I think he's got I think it's still going. What's it called? 24/7 it was, and then it went down a bit, so I don't know what he does now. Discord. He's never been invited to the Blue Marble science get-togethers. Strange. I don't know what's happened to that. There we go.
Now today I'm going to have a look at a video on Nathan Oakley's channel where 10th Man talks about navigation. Now he is one of their fake experts on the sextant and navigation.
He called him a fake expert on the sextant and navigation.
But what I'm going to do is demonstrate how lack of scientific reasoning is leading him astray. So let's cue up the music and get going.
Lack of scientific reasoning. Sounds like our sort of stuff, doesn't it?
Strange words in his mouth.
So a lack of thinking in terms of cause and effect
is what's I think 10th Man's fault. I don't know. Here we go. Listen to this anyway.
Now I'm going to start off by going over this diagram that Nathan has up on his show right now.
This diagram, I might be able to put it up in a moment. Let me get a
from Mick West.
Yeah, it's Mick West. He doesn't say that, but obviously.
But it is.
It is. It's Mick West's drawing. I mean, that's why Nathan's got it up, right? Because they're going over it. But Bob doesn't say that it's actually Mick West. And this is really, really good when you listen to this. So there you go. Everyone can see that he's got Mick West's drawing with eye level and surface level.
And I'm going to try and have a look at the diagram to see where their misunderstanding lies. So let's go ahead and have a look at the concept of a 90-degree angle on a curved surface. Now this
The concept of a 90-degree angle and a curved surface.
This is just
It's Mick West's drawing.
yeah, weird concept because these angles cannot exist.
And what he doesn't mention at all is surface level and the drop, the nutsack drop. He doesn't mention those at all in this. This is genius.
seems to be something that they have an awful lot of trouble with. Now, if you look at this purple line right here, this represents the curved surface of the Earth. Okay? It's an arc.
It's a drop. That's what he's going for.
Over the surface of the Earth. Now, here is our observer location right here. Now, you'll notice that he has a line marked, this dotted line that says surface level. Now, that touches the curved surface of the Earth at one point.
Right? So, the one that he's got marked surface level is the one that's parallel to the one that he's got marked eye level.
And that would be his location. Now notice that there is a straight line going directly above that point at a 90-degree angle to the surface level.
90 degree to the surface level, which is a straight line.
The surface level is a tangent. Now it's a basic tenet of geometry that if you draw a line perpendicular to a tangent, you have a right angle. Now,
do you want to go over that?
Yes, we always say that you can have
Did you hear what he said? Yeah.
to this.
If you draw a
surface
line
level.
perpendicular to a tangent, then you will have a right angle.
Yeah.
Yes,
that's true.
because a tangent is a straight line, and any perpendicular to that straight line will be at 90 degrees to it. I mean, what you've just heard is a confirmation of a statement of perpendicularity said by this man. I'll go back and put it again because it is quite amazing, really.
Angle to the surface level. The surface level is a tangent. Now, it's a basic tenet of geometry that if you draw a line perpendicular to a tangent, you have a right angle.
It's a basic tenet of geometry that if you draw a perpendicular to a tangent, you have a right angle.
Only to a tangent.
Well, any straight line, really. If you draw a perpendicular
Yes,
to a straight
I'm
line,
joking.
then you have a right angle. I mean, the guy's a genius. So yeah, that's a basic tenet of thingy, and he's also got surface level as being a tangent. Is that?
Yeah, but this is strange name because this is not a surface of anything. So, but
Well,
okay.
Yeah, but I mean, I've heard other people say that the horizontal is a tangent. But in that case, that would make surface level equal to horizontal, wouldn't it? Like level would be
Obviously.
horizontal. Bob's just said that, surely. That's how you have a perpendicular to a tangent, and that's at right angles.
Yes, we have two lines labeled level.
Yeah.
Surface level and eye level. So, and they are both horizontal.
And the perpendicular would be the drop. I mean, let me just get another picture of that, because we've got this weird dude on the screen, haven't we? So you can't really see what. Put everyone on there. I don't want to do you out of it, but I mean, we are under threat of a copyright strike because this guy thinks that all of this is his if he talks about it. But as you can see, it's just a picture. It's Mick West's from Metabunk, is it? Metabunk curve calculator?
Yeah,
This
something
is,
like that.
yeah. And these lines, he's talking about this surface level and the eye level, these two lines here, that's what he's saying is a tangent. But I mean, this is all fantasy, this stuff down here, really. If this is surface level, a dotted line. Obviously it goes to prove that level is horizontal, even in the minds of people.
Now, whether that tangent is located here or it's located at the horizon going straight up this way, there would be a tangent line going like so. You can draw a right angle there as well. And when you get down here to the target, notice that there's also a tangent line here, and this is a perpendicular line to that tangent as well. So there's a right angle between here and the surface at the location of that tangent line.
There
No.
isn't. There just
No, it
isn't.
isn't.
Like
Yes.
it's
That's a
fictional.
rumpus.
He's just making that up, right? It's not actually there when he's doing it.
Yes, at
Fantasy.
least we have surface level, at least this dotted line, but there is no tangent here. So he's equivocating this first tangent to this second example without any tangent. And he's saying that this is perpendicular to a curve. No, it is not. It would be perpendicular to tangent at that point. Yes, but there is no tangent line here, so it is not perpendicular to curved surface.
That's a rumpus pull there, right?
That drop, yeah, that's the drop
Because
from
drop
from the surface level is your your rumpus pole. Complete fantasy. We've got a guy in the chat called Howard Moore says, "Lol, Bev still trying to redefine geometry. What a waste. You all have fun." This is Howard. This is Mick West's curve calculator. I'm not trying to redefine anything. We're just going over an old video. I think Howard Moore, does that sound familiar? Is that the one that Geo said he didn't want people talking about? Like he said that was doxing or something. I don't know. Might be doxing himself by posting that. Sorry, Howard. Was I not meant to read your name out? Or are you bringing that character back for a bit?
Notice that there is a chord distance between the 2 points, and there's a distance along the surface of the Earth.
Right, so we're setting it up now, right? If you guys can remember, there is a problem that sent Bob away for a short break a bit ago, and that was to do with a straight line, right? Shorter than a straight line, and this is where it starts creeping in. You might see it, you might not, who knows. But
distance along the surface of the Earth is longer than the chord line. Notice too the sagitta here, which is also called the versine. And by using the sagitta or the versine, we can get an idea of the relationship between the chord line and the line across the surface of the Earth, which is an arc. Now, this is why conspiracies in many cases are not a knowledge deficit problem.
Conspiracies. There's a conspiracy here somewhere. And I think it's the conspiracy of having a shorter than a straight line developed through, I don't know, whatever's going to happen in a minute. So apparently there's a conspiracy somewhere.
He has the information right in front of him. He's just not connecting the dots in his head to realize what that information is showing him.
So he's saying that somebody else isn't connecting the dots to see what the information is showing him, as he shows a drop that is perpendicular from surface level, and completely missed it. Didn't bother saying anything about that. The fact that it's Mick West's curve calculator drawing from. He didn't mention that the drop perpendicular to the surface level, or as we call the rumpus pole, that's your separation of level from horizontal, right? That's what a rumpus pole is, except the line that normal people would call horizontal, this guy's labeled surface level. So how can you have a separation of level from horizontal if level is the straight line? Bob can't see it. There's a problem. He's not aware of that very fact that he's got surface level being a straight line in his drawing that Mick West's given him. Mick West isn't around. He's like Jesse Kozlowski. He's done a Jesse Kozlowski. He's left people with these paralogisms that they're just having to live with. And it's obviously causing problems. There's a perpendicular problem, obviously, vertical, horizontal. And that's going to come back around for quite a while. But this is the shorter than a straight line development. And it's classic.
As we'll see, this is a very common problem in the Flat Earth conspiracy. So let's have a listen to Nathan and the 10th man talk about navigation.
Nathan, I've got a few more slides on the topic.
Right, I'll have to get this. It's got a few more slides on the topic. This is 10th man at Nathan Oakley's doing this picture. It's not what I choose to do, but I mean this is to show everyone the mess that people get in. Right, so there's the picture. And here we go.
That we left after the pre-show. Tell me when you're. I'm going to get to it myself.
Okay, I'm there. Great circle.
Yeah, give me a second. Hold on. There we go. Okay, so you've got, go to the bottom. Start from the bottom. New York to Paris.
Okay, ready when you are.
Yeah. So you want to go from New York to Paris. In the straight line, it's 3625 miles. In the circular dotted line there is 3786 miles. But here, they're a little trickery because the straight line is their curved line, and the curved line is the straight line.
He's got some text on.
I'll explain. Next slide, please.
The shortest distance between any 2 points is what's called a great circle.
Right, so you've heard commonly, mainly spoken around here, we say the shortest distance between 2 points is a straight line. That's what we say. Oh, that's what I say. Euclid defines it slightly different. Everybody can define it for themselves what a straight line is. Well, I say it's the shortest distance between 2 points. Not so for other people. I'll put it back a little bit.
I'll explain. Next slide, please.
The shortest distance between any 2 points is what's called a great circle.
See, now, I would say a straight line, but Bob here says the shortest distance between 2 points is a circle, a great circle. That may be one of his problems, but I mean, I think a lot of people might have that problem. It becomes, this is the straight line problem, and how the mind can be affected by just a straight line.
And that's like stretching a string from New York
problematic.
Paris. If you pull that string tight, this is the course that you will take. Now, the difference between this and what's called a rhumb line is that notice the angle the great circle course crosses this meridian. Now look at the angle here, and the angle here, and the angle here. Do you see how the angle changes? Now, with a rhumb line, you cross each meridian at exactly the same angle. Now, the difference between a great circle course, which is the shortest distance, and a rhumb line is one of convenience. With a rhumb line, you can set a compass course and follow that compass course all the way from New York to Paris, because it crosses each meridian at exactly the same angle. You'll notice the difference in distances. This is 3625, and this is 3786. So it's about 160 miles difference on an almost 4,000 mile journey. That's really not all that much if time is not of essence.
There is a difference, but does time come into distance measurements? I'm not too sure. Seemed like a bit of a non sequitur there from Bob. But you can see that there are two lines, and there is becoming a problem already within the mind of where we go from this. This is the development of a shorter than a straight line distance.
And if you don't have the ability to calculate this course, it's much easier simply to follow the compass bearing. This is why the Mercator map was developed. The Mercator map was developed in such a way that you could draw a straight line from New York to Paris, and it would cross each meridian at the same angle. It projects.
Just so you could draw a straight line from New York to Paris. That's why he thinks the Mercator map. I mean, I tend to use maps from reality, scale maps. These world maps that these guys like to think of aren't accurate, so it's not much use to be using them as an example.
I would agree, but still, I have read about description of Mercator's projection, and that's correct. This is purpose. Supposedly, it was purpose for him to draw this projection to make drawings easier for navigators, because they want to draw lines on the map, and it is easier to just draw a straight line instead of curved line. So this is what I've read on this description.
Yeah. Go for a little bit. It's really hard work. This is part of I think the problem around this. When you hear somebody saying something that just doesn't make sense, that information doesn't go in. It's nothing. It's like he's babbling. But this is dogmatic, but to absurdity, really. Like, he's put himself within a model and not sacked himself.
Projected the spherical Earth onto a grid map, and by plotting a straight line on that grid map between 2 points, you plotted a rhumb line. To get the great circle route, you have to do something like the Haversine formula, and then you.
It says if you make a grid map and then draw a straight line on that grid map, then it's actually the run line, and the run line is the one that he's got as a curved line. So when you draw a straight line on a grid map, you're actually drawing a curved line to Bob. He's getting his straight lines and curved lines all mixed up. Let him say it again.
Circle route, you have to do something like the Haversine formula. And then you actually plot waypoints along the course that says, okay, well, I'm starting off on this compass bearing. In 100 miles, I'm going to change to this compass bearing. And that's the way you would follow a great circle course. And if you only had a compass for navigation, you could follow a great circle course by plotting out those waypoints and what your bearing would be from each of those waypoints. Now we just plot it out on the spherical GPS map, and it puts a little magenta line down on the surface of the Earth, and we just follow the magenta line. That keeps us right on the Great Circle course. Now, right here is a really good example of not understanding the scientific concepts or the reasoning behind science. Now,
right, this is a great example. Remember, this guy calls himself Bob the Science Guy.
I have no idea what he was talking about as a good example of being not scientific.
Yeah,
example.
I think he's going to go now. I think this is the one he's going to
Great Circle course. Now, right here is a really good example of not understanding the scientific concepts or the reasoning behind science.
Right, it's a not that, right? It's a great example of a not understanding science. So it doesn't actually have to explain understanding science and reasoning and stuff. He's explaining a not that.
And which science he's talking about?
Who knows? We'll probably go over it. Probably something geometric science. I don't know.
Now, 10th Man has put up 2 slides so far. The first slide showed that a great circle distance is the shortest distance between any 2 points on Earth.
See, again, it didn't.
He didn't say that. He said that we have all curves. So he's misrepresenting, I think, him.
I think
Tenth man.
Bob did that. I think Bob put that they're both curves. But what he's saying is that 10th Man said that the shortest distance is a curve, a great circle, but it's not. The shortest distance is a straight line. That's
Yes, and the
blatant lie.
10th Man didn't say that on this clip.
I know.
At least.
Yeah, he's just making it up. Put it back again, just so you can listen to it. Right,
2 slides so far. The first slide showed that a great circle distance is the shortest distance between any 2 points on Earth.
No, it didn't. Maybe to the mind of a model afflicted person, but it just didn't.
It is shorter than a rhumb line. And then he goes and puts this slide up and says, okay, well, if you stretch a string across the surface of a sphere between 2 points, that's the shortest distance between those 2 points on a sphere, a great circle. He just got done saying that the shortest distance between 2 points on Earth is a great circle. He's not making the connection that if the shortest distance along the surface of the Earth is a great circle distance, the Earth, by definition, must be a sphere.
Well, this is just circular reasoning.
Yeah, but the shortest distance in reality between 2 points is a straight line.
Yeah, if you stretch the string on the ball, it doesn't prove that the shortest distance between 2 points is a curved line.
No. No, but that's what Bob's thinking, right? Bob's got it in his head that the shortest distance in reality between 2 points is a great circle.
Yes, and he's calling this science.
Yeah, it's a great example of not understanding science, which I suppose it is, really. Model affliction. It's a great example of model affliction.
Now you would have to add a caveat to that, and that is that the shortest distance at any location in any direction along the surface of the Earth is a great circle.
Doing that, you have to add a caveat that it's
Even
always
two.
a great circle, right? In any
Even
direction.
two.
Yeah.
Yes, in all directions and on the surface of the sphere. So you have two caveats, not one.
Any location in any direction. The shortest distance along the surface of the Earth is a great circle distance. The Earth, by definition, must be a sphere. Now you would have to add a caveat.
Definition.
Yeah, but no,
Not by
he's
definition.
adding a caveat now, right?
To that, and that is that the shortest distance at any location in any direction along the surface of the Earth is a great circle.
But he put surface level. He's just shown a picture of Mick West that said surface level, and that was a straight line.
Yes, and he doesn't know what definition means because he said that something is by definition. No, curved lines stretched upon a ball does not define, don't define shape of the Earth. Sorry.
And shortest
this is what he said.
distance between 2 points is a straight line. Known to be. But
Which of course is the case. But do we really need to go into it that deeply when we've already identified the key issue in his reasoning? He doesn't connect the concept that the shortest distance between 2 points on Earth is a great circle and the shortest distance between 2 points on the surface of a sphere is a great circle.
like it,
And I can say why.
That's circular reasoning, right?
Yes, I can say why 10th man didn't connect.
Yeah.
Because he didn't
say
assume
either.
sphericity. Yes. He didn't beg the question about shape of the Earth. That's why he didn't connect. So do I.
So I have to put that again because this is a great understanding of a not understanding the scientific method by a guy that's just going to give you a circular reasoning fallacy.
Any location in any direction along the surface of the Earth is a great circle, which of course is the case. But do we really need to go into it that deeply when we've already identified the key issue in his reasoning? He doesn't connect the concept that the shortest distance between 2 points on Earth is a great circle and the shortest distance between 2 points on the surface of a sphere is a great circle. It's just going right over his head.
He doesn't connect it, and I wouldn't have connected that either because I know that the shortest distance between 2 points is a straight line.
Yes, and he is making equivocation between line on surface of Earth and line on surface of the sphere. So he's not proving that the line on the surface of the Earth is the same as the line on the surface of the sphere. He's not proving that. He's just stating. He's just
straight line
equivocating
distances,
that.
right?
Yeah,
Like, they're
but
not curved distances. It's a straight line distance from A to B. Everybody knows that. But Bob's here trying to tell you that that's curved. And because it's curved when it's on a sphere, then that proves that his fantasy of a curved line equals a curved line. But it's not.
Yeah.
It's a straight line in reality. But this is where people get come unstuck, right? Because Bob is going to imagine at some point that there's a shorter than a straight line distance. Because he's getting mixed up between straight lines and curved lines. Because in reality, there is a shortest distance from A to B, and now that's a straight line. Yet Bob thinks it's curved. That's what he's laying down.
Because he's trying to promote this narrative in his science denial conspiracy. Let's listen to some more. Now, first of all, the rum line is not a straight line. The great circle is a straight line. You've got it backwards.
A great circle is a straight line. Like, see, the problems are building on top of themselves for people. That was Bob that said that. I'll put it back again.
The rhumb line is not a straight line. The great circle is a straight line. You've got it backwards.
No,
The rhumb-
it is not.
You've got it backwards. He says.
Yes, he got it backwards because
Yeah.
both lines are curved.
They're both on a sphere.
Rhumb line is a straight line only on a Mercator.
Let me get that.
They have just the curvature at different rate, let's say, but still both are curved.
Projection, but I do want you to have a look at this rhumb line. Look at where it crosses the up and down meridians. You see how that angle remains the same all the way along until it spirals in?
It's not an angle, is it? How can you say that that angle stays the same?
Or
It's a
in
spiral.
reference to what?
So one of them's a curved line. And he says the angle stays the same of a curved line. It's crazy.
To the
Yeah,
pole.
completely crazy.
Now look at the great circle distance. Right here is very obvious. But if you look at the great circle distance and compare it to the lines of latitude, you see how they're different? You see how the angle here, it's coming up into that meridian, and here it's going down away from the meridian? That's the difference between a rhumb line and a great circle. The shortest distance between any 2 points on Earth, as well as on the surface of a sphere, is that great circle distance.
Their presupposed model, if you go southerly, you end up at the southern pole. That's their straight line. But the great circle, that's the shortest route. That's the curved line. Now notice the switcheroo here. All right, next slide, please. So what is a great circle? A great circle is anything. Now this is presuppose. It's all make-believe because you got to assume you're on the globe, and we just went through housekeeping. There's no R. We don't have any radius value. But if you were on the globe, a great circle would be this great circle with the yellow meeting the red, and it goes all the way through the center of the Earth.
You know, despite all of his rhetoric and his presupposed and no radius and everything, this is obviously testable. How could we test the idea that the great circle distance is the shortest distance between any 2 points?
It's testable.
Oh,
That's
yeah.
great,
How?
isn't it? Yeah,
How?
how could we test it? It's a good job he's asking the question.
Let's do science.
On the Earth? Well, we can actually measure distances across the ground. Now,
We can actually measure distances across the ground, right? Remember,
Mm,
short break
that-
coming.
that sounds like real science.
recently I had a trip from Florida to Michigan, and I calculated the distances between those 2 points, both on a flat plane using triangles and on a spherical surface using the Haversine formula. Now, I can actually
Right?
I'm disappointed. I thought that he will say, for example, I had with me a steel tape, a very long steel tape, and it was rolling across
He's
my
got a
way.
car. He's got an
He has formula.
odometer. Yeah, but he's calculated them first. That's pre-planning, right? He's doing his car. He's going on a road trip. He's going on his holidays. He's going to the beach to do his land sextanting. And I think he dropped off at Blue's. Him and Blue got together to do a bit of weighing weight as well on this trip. It was a great trip of 2020-ish. I can't remember how when it was. But yeah, he's going to drive a car.
measure the distance between those 2 points. And guess which distance it matches? The flat Earth distance? No. It matches the great circle distance. Now, the other thing that's very interesting.
It's shorter than a straight line, but this is the basis behind what's going on here.
Testing is if you know the distance between those 2 points, you can actually calculate the Haversine, which doesn't involve the radius. That's just the angle of the arc. And you can use that to calculate what the radius of the Earth is. And I successfully calculated the radius of the Earth.
He successfully calculated the radius of the Earth along his trip while he was doing his Haversine. Well, he's very clever.
Now that goes along with all the other ways that we have to calculate the radius of the Earth. The Eratosthenes experiment, Al-Biruni. We can even calculate the radius of the Earth based on how much weights change with latitude, because that has to do with the angular velocity of the rotation of the Earth. And the thing about science is that we have scientific concordance, and that means that even though we calculated the radius of the Earth by Eratosthenes, Al-Biruni, rotation of the Earth, and distance across the surface of the Earth, they all come back to the same radius.
You want to go back over that again? That scientific concordance of these
like scientific
shadow giants.
consensus. Yeah.
Yeah, it's shadow giants. So
Scientific concordance, and that means that even though we calculated the radius of the Earth by Eratosthenes,
illogical. We've had Betty come round to show that. Completely illogical way of deriving anything. Right? Pre-assumptions. Too many to count. Ridiculous pre-assumptions.
And in his assumptions, there are already circular reasonings. So.
Yeah. And who's next?
Al-Biruni.
Al-Biruni. The angle trick, right? The great angle trick. The first of perhaps one of the great angle tricks. And it's still going today. Al-Biruni measured a mountain flat, apparently. I've heard somebody say. Who else?
Rotation of the Earth.
Rotation of the Earth. You can.
That's strange.
Measure or calculate the radius from the rotation. You know, plumb bobs don't work with any motion. Well, hey.
And distance across the surface of the Earth.
And distance across the surface of the Earth, which is a straight line. Jesse Kozlowski, 3 coplanar points.
They all come back to the same radius. You know, they have a chant that you need R for that. Well, we have R. So I guess that solves that problem, eh?
Yep. That's all right. We've got R. You can have that.
Yes.
Now,
R
the other
from
thing that's
triangle.
Sorry, yeah. R, yeah. Just get R.
This is new science. R from triangle.
Or from a circle.
Important about this is by using the great circle distance and the radius of the Earth, which we obtained by other means, we can calculate the distance between any 2 points.
You can calculate the distance between any 2 points. You can just measure it. You're normally best off. In order for science, right, you need to be able to measure it. Like, there's no check without an actual measurement.
You can do the same thing on a flat Earth using triangles, connecting your starting point to the North Pole to your ending point. You can calculate that leg of that triangle. That doesn't match with the actual distance between those 2 points on the surface of the Earth.
You can... I want to hear that again. Because, I mean, I know he's talking about flat Earth, but he's just talking about triangles, really.
On a flat Earth using triangles, connecting your starting point to the North Pole to your ending point. You can calculate that leg of that triangle. That doesn't match with the actual distance between those 2 points on the surface of the Earth.
You see that eye
Why?
touch?
It's strange because he's saying that one set of calculations doesn't match with other set of calculations. What can it prove? I would say nothing. But okay,
Why do you have to go to the North Pole to get a triangle? Like
I have no idea.
Nobody does that. I don't know why.
I would
you
say
get
that that would be dangerous and impossible.
On a flat Earth using triangles, connecting your starting point to the North Pole to your ending point. You can calculate that leg of that triangle.
If you go in, I don't get that. I don't like that. Again, troubled minds, I think. You're going from A to B, then just measure from A to B. Like, why do you have to go to the North Pole?
That doesn't match with the actual distance between those 2 points on the surface of the Earth. The Great Circle distance does. Now let me show you another problem that the flat Earth has.
The way he does this, right? You show him a problem that the flat Earth has. I mean, they're obsessed with these other models. Like the flat Earth's. Well, I don't know who he thinks has this problem, to be honest.
That line, the red line, is very clearly curved. That is the Great Circle distance between Santiago, Chile, and London in the United Kingdom.
Right, so the Great Circle is curved, says Bob.
Now let's go ahead and rotate the Earth so that line is directly underneath us.
Directly underneath us.
Oh, now it's straight.
So
Seemingly.
it's the line that was curved a moment ago.
Now it's straight. Yeah, this is the only trick they have.
Well, no, this is a problem that the flat Earth has, according to Bob. Right?
Why?
Well, you might hear it. Look.
That looks pretty straight to me.
It's a curved line, though.
So here you go, flat earthers. Straight line, curved line.
It's curved line. It's still
straight
curved.
Line, curved line. A basic inability to comprehend 3 dimensions.
Whose basic inability to comprehend 3 dimensions? The line doesn't change from being a curved line.
I would say that there are some people who just don't. They are not fooled by this idiotic trick. And he calls them that they cannot comprehend. Yes, we can comprehend this trick. This is idiotic trick.
I can't comprehend the stupidity of somebody thinking that other people can't comprehend it. Like that's the bit that I can't comprehend. Is what Bob's going on about. It's just fantastic.
He's showing idiotic trick, and he has some, let's say, complaints that people don't eat that trick.
I did clip that and turned it into a 30-minute video of him just going straight line, curved line, straight line, curved line. And he copyright struck it.
And this is something that you have to have in order to do science. You need to be able to visualize things in 3 dimensions.
In order to do science, you need to be able to visualize things in 3 dimensions. Like actual in reality, right? You need to have the thing to do science with. Is that what he's saying?
Yes, and by the way, in 3 dimensions, it is obvious that this red line is curved.
It's curved, yeah.
No matter in which position you will put this line, it is curved line.
You'll know it's curved, right?
If it is curved, because it is on the surface of the sphere, it is curved, it doesn't matter how it looks, because from different angle in perspective, you can see different angles. So this is no problem. But we know that this is still curved line.
Yeah, your scientific brain should be able to reason that the curved line on a surface of a ball won't change into a straight line. Right? But surely a scientific reasoning should be able to comprehend that.
Yes, but for Bob, this is a fallacy of some people.
Well,
Flat
I think,
earther
yeah, he
and
imagines other people have as a problem, except Bob might be the one projecting, right? Because Bob's the one that has it as a straight line. He's already said it himself. He thinks
yes,
the great
maybe
circle
he's
is a
okay.
straight line.
Maybe he's okay. Maybe he's tricking himself. I don't know. But if he is tricking himself, that means that he's very not well.
Yeah.
It's very clear from this example that they can't. They can't comprehend the concept that if you have a curved line on the curved surface of the Earth and you rotate that line so it's directly underneath you, that looks like it's straight. You move it off to the side a little bit, it's curved again. This is a foreign concept to them.
Like, I don't know what he's trying to say here, but it's obvious that this is a troubled man.
Yes, he's saying that this is concept, but this is idiotic concept. So why would people take that idiotic concept? Because now he's showing just childish trick he's trying to project on others. I don't understand. He's very troubled here and strange.
It looks like he believes that lines are observer dependent. From like one person, a straight line straight, but from another person, it's a curved line that's straight. Depending
Yes,
on where, yeah, like
yes.
somehow it doesn't exist. There's no such thing as a straight line. It only determines who's looking at it and from where.
Yeah.
Yes, but in that way, he's denying objective reality.
Oh yeah, big time. Yeah, because he's basically saying reality depends on the observer, not
Relative.
real.
It's like a
Yeah,
relative
everything's relative.
position. That's
Yes,
what
this is what
talking
he's
about.
saying. Yes, he's saying that this is dependent on observer. So you can change reality. You can change a straight line into curved and vice versa because you are changing your position.
Yeah.
Or position of this line.
Is it just that, like this is his broken mind that he's wanting to just sort of put out there? Because he can't, he's not trying to do it as a teaching video, is he? Surely. Like it sounds to me like a cry for help rather than a teaching, right? Because he can't expect people to not know that if it's a curved line on a ball, then it's a curved line on a ball. It doesn't turn into a straight line if you walk around the ball.
Yeah, interesting. It is Global Hug Day. Maybe this is his cry for a hug. He just needs a hug.
This is yet another example of the illogical reasoning that conspiracy theorists and science deniers tend to use.
Illogical reasoning. Like where?
Okay.
Where in that? That's terrible, isn't it?
So this rotating globe with a red line, for him, this is logic. What that curved line is changing into straight and back and forth. For him, this is logic, and some people deny that logic. This is terrible for me.
Yeah.
Real. He's in real trouble here.
This is an old video. But it's called Talking to a Science Denier. Faulty Reasoning. He's titled this video that.
So this is his science. This rotating ball with the red line, this is science.
Yeah.
This is just terrible. Just terrible.
I got on to Nathan Oakley's after show, and I specifically invited the 10th man to come join me today. He decided to decline in favor of calling me a name. But the invitation was there, and it was a polite invitation, and he could have sat down and discussed some of this stuff with me now, but he chose not to. Probably a wise decision on his part because nobody likes to be made to look foolish. Now, if for some reason you think I'm being unfair with this, let's listen to him say it again. I don't think he understands the concept that when you put a great circle directly underneath you in the center of the earth, it appears to be a straight line.
He says it again.
Yes, we know that it appears to be straight line, but also we know that it isn't.
Yeah. Yeah, we know what it looks like to you, Bob, but we understand that it's a straight line as you're looking at it, but it's still a circle.
Yes, and I can give another example. If we have representation, let's say, of straight line, of course, in reality, we cannot have perfect straight line, but that's something similar, like very, very straight stick. And if we can turn it in front of our eyes in specific angle, we can see only like a dot. So, but it doesn't mean that we turned line into a dot because of some angle of our vision. It is still straight line. The same with this curved line. It can be seemingly straight, but we know it isn't because it cannot be on a sphere.
Like a laser dot sight, right?
Yeah, the same thing, yeah.
You see the dot at the end of the laser beam.
Yes, but between laser and this surface, it is a line, of course. So the light has to pass this line between 2 points.
Which would be a straight line, not a curved line, like Bob thinks. Doesn't matter how you look at it, it's straight line.
My assertion is that a great circle is the shortest distance between any 2 points on Earth.
See? Said it again.
Assertion.
His assertion.
Center of the Earth,
assumption. Begging
it
the
appears
question.
to be a straight line. My assertion is that a great circle is the shortest distance between any 2 points on Earth.
Well, I'd say that the shortest distance between 2 points is a straight line. So we've got two different assertions here, Bob. Challenge, easy. Science could definitely decide that. The shortest distance between 2 points, in reality, is either a great circle or a straight line. Science test. And it's Bob's assertion that it's a great circle. I say it's a straight line.
If you are directly over that great circle, it will appear to be a straight line.
But it wouldn't actually be a straight line. Otherwise, you'd be calling it a straight line and not a great circle.
By the way, if he's going with assertion, i.e. assumption, so why even he's now trying to prove anything? Because outcome, it will be always the same for him. So why he's trying to prove anything? It's just strange for me.
If you are off-center to the great circle above the surface of the Earth, it'll appear to be curved because it is indeed curved. It's following the curve of the Earth, but when it's directly underneath you, it's only in one dimension, that vertical component.
See? What?
One dimension.
Don't even understand what that means. It's only in one dimension, that vertical component.
He's just rambling.
Well, yeah, but I mean, he's just said that, you know, there's a difference between a straight line and a curved line. And when you're looking at it in a different place, he says there's... Listen to it again, because this is...
Following the curve of the Earth, but when it's directly underneath you, it's only in one dimension, that vertical component.
It's only in one dimension, that vertical component. What?
I don't really understand what he said.
That's a nothing, right? It's a vacuous statement. right? A meaningless statement, vacuous in that regard.
And you don't see it go left or right. But let's let him go through it one more time.
It shows the great circle is a straight line and the rum line is the curved line. Now go figure how they can switch you every time they want this nonsense. Because what they're trying to say is that the great circle, the slide previous with the yellow dotted lines, a continuous circle is a straight line. So on the very next slide, they'll show that as a straight line. And the rum line, the actual straight line, is the curved line on the globe. What nonsense. You need R for that first.
Well, it's a good thing that we have our 10th man. But, you know, even if we didn't have R, the great circle would still be the shortest distance across the surface of the Earth, because the Earth is a sphere.
I'd say the shortest distance between 2 points anywhere on any surface or whatever, the shortest distance would be a straight line, because it would cut whatever surface you had. Like if you have air, if you have a bit of land and then some air or whatever, it's always the shortest distance between 2 points is a straight line.
Yes, so even on this, you cannot draw a straight line on a sphere, so you will have to cut off a spherical cap, let's say. And you have distance between 2 points on the sphere being a chord line, straight line. Simple.
Yeah.
Getting right down to the nitty gritty. It's not just we've been deceived. Here's the deception. It's here's how you've been deceived. I love it, 10th. You're getting right into this.
Oh, there's so much more. It's just getting through that. Like I said, the first thing was making sure I knew how the sextant worked, and that was going to be the kill-all of all kill-alls, because if it can't work on the curved surface, it's over there. But then how do they trick the navigators? How come people using the sextant can actually believe it is working on the curved surface? So that's the stuff I'm into now. And there's so much minutia there. I have to watch video after video. I've ordered 9 books from eBay on this subject that will be coming in the week. I have quite a library accumulating here on this. Eventually, within the next 2-3 years, every segment of this will be dissected.
Oh, dear. You know, 10th man, every single one of those books that you ordered, if you actually would read them, they'll tell you that the sextant works because the Earth is a sphere.
Now, they'll say sextant is an angle measuring device, and mathematically everybody should know the basics that you can do fuck all with an angle.
But still, you require straight lines.
Well, it's just an angle measuring device, right? You just need 2
So,
points.
but he said that but Bob said that it works on the surface of the sphere. No, it will not work.
No, he said the books, I think, but let's listen.
Every single one of those books that you ordered, if you actually would read them, they'll tell you that the sextant works because the Earth is a sphere and celestial objects are very distant, and as a result, their light arrives at Earth in parallel.
That's not a sextant. Is just an angle measuring device, and it works because it measures an angle between 2 points.
Yeah, in straight lines.
Yeah.
So it has nothing to do with the sphericity or not sphericity of the Earth.
Strange. Model affliction, no.
That's the only way that a sextant works. It doesn't work on a flat Earth with a...
It just measures angles, Bob. It's not a us and them thing. In reality, a sextant measures angles.
Local sun. It just doesn't. But will you realize that? How many times do you have to be instructed? This is the problem that you run into when you deal with a flat Earth and other conspiracy theories. They don't want to believe the evidence that's right in front of them. If they have a book that tells them that celestial navigation requires a spherical Earth, they'll say that it's some sort of a plot and they'll just buy another book. Well, when that book tells them the same thing, Well, that's a conspiracy because two different authors are conspiring to mislead him. So he'll get a third one. Now it's going to be 3 authors. And it doesn't.
You don't need to read books to understand that a sextant just measures angles. And you can read into that whatever you want.
Doesn't matter how many n plus 1s he goes to. He's going to get the same answer because it's the truth. That's the way celestial navigation works. It works on a spherical Earth. It works on a rotating Earth. It works on a spherical rotating Earth with very distant celestial objects such as the sun and the stars. Reading another book or making another video or looking at another flat Earth video is not going to change that 10th man. Now you've already looked into the sextant a little bit, and we're going to have a look at your videos on the sextant because they're hilarious, because your misunderstanding of the sextant and celestial navigation borders on absurdity. And quite frankly, it is a little humorous. So we're going to go through those as well, because quite frankly, you and Brian's Logic and Mitch from Australia are my new hobby.
Got a hobby about men.
I
It's done
know
a
that
bit
was
ago. That's pretty gay, right?
his hobby. Like, really, you got? Is he supposed to be some sort of highly intellectual person? I mean, generally, people I know who are really smart with all these degrees have very complex, interesting hobbies, like modeling trains or whatever.
Yeah.
His
Calls
his
the
is
10th
based.
man a fake expert, but I mean, he's taking the role of governor. It didn't last long though, did it? He's at the bottom end of his garden now, looking at lights in the sky. Like, it's my understanding that celestial navigation, I mean, on land we use maps and use road maps usually if you're going from A to B, and in the old school it used to be actual maps, but now people have got maps on their phones that tell them where to go. So there's not much need for this celestial navigation, looking at lights in the sky. It seems to have been brought back in, and it's an ancient thing, but they've brought it back in, measuring angles to prove shapes, but it can't be done. The basic geometric principles just cannot be done. And Bob's having a go at a group of people as well, and it seems like he's unaware of the basics.
This is Bob the Science Guy signing out from Northern Michigan. Thank you very much for your time. I hope this was somewhat enlightening, and if you have a moment, hit that like, subscribe, and ring the bell icon for my channel. Now, if you'd like to be a member of the channel or a Patreon or just support us occasionally with a PayPal donation, all that money goes to buying new equipment for the channel to bring better content. One example would be this marine sextant that we use to find noon sightings and learn a little bit about celestial navigation.
He uses them to find noon sightings.
Yes, and he said that he hopes that it was enlightening. But I think that for me, most enlightening was this curved line, straight line, curved line, straight line. That was very, very learning.
Well, don't forget that there are videos out there where Bob, this man, said that a shorter than a straight line distance. He thinks that the rhumb line is a straight line, but the great circle is shorter than the straight line, whilst in turn it not being a straight line, but only being a straight line if you position it in a certain position. But he imagines that that's shorter than a straight line.
Yeah, but this is for me another problem, because if this curved line is making a straight line also in different position, it means that it is shorter. So it means that the same line is shorter and longer. It is dependent on our position of viewing, which is of course absurd. But this is implication of what he said about this great circle in certain position. When looks like straight line, it should be shorter than the great circle then, but it isn't, apparently. Complete nonsense.
I think that might be a sock in the chat. You know, these ones that have like multiple sock accounts. Catman, I think.
Tomcat? What is the tomcat? Come?
Yeah, I think so. Yeah, I think so. I think that would be Bob. And the greatest of the shorter than a straight line. This is what happens. If you imagine that a great circle is the shortest distance between 2 points in reality, then you've already got a skewed idea of a straight line. And so then if you can imagine that another curved line drawn on a sphere is a straight line, then you can imagine that one of your curved lines is the straight line that's less than the other one, whilst completely giving up the idea of the actual straight line that applies in reality, right? Obviously. This is the concept of the breakdown of why people have problems with a horizontal being a straight line and the perpendicularity of the vertical and horizontal. It's very simple. People have problems with straight lines. Model afflicted people have problems with straight lines. Don't want to put this on everyone. But most people understand that in reality, a straight line is an actual straight line. But there are some people, like you've just heard, they think that straight lines apply to different models differently. And that's where you get stuck. Because people imagine straight lines as being straight. Normal people, at least, anyway. That's better, Blue. You should get Bob over. Remember the old times where you used to go measuring weights? He did that one. I think that was you and somebody else that he got in with that. The road trip, the great road trip.
And by the way, what we learned about great circles, we learned that they are curved. So this is what we learned from this video. Thank you very much.
Yeah. And the fact that you have to get above them in order to look down on them for them to become
and
straight.
We also learned, not very much because I knew that before, but we learned, or some people could learn from that video also, that curved lines can be seen as straight from a specific angle. Yes, that's true, but they are still curved.
Yeah, but I mean, I bet you thought you could look at it from the side. Bob says you've got to get above it.
No,
the
okay,
positioning has to be above. Yeah, but in order for you to think of it from the side, then you're placing yourself incorrectly. You have to be above. Right? There is a conceptual thing, right? Because if you're
Yeah,
at the side of it, then you're not thinking of a great circle. You're just thinking of a line on a ball. A great circle is
You have to be exactly above,
yeah,
as a matter of fact. Not
because
1 inch to the left or 1 inch to the right.
well, he's
yeah,
not.
Is
He's
that
not
appearing?
associating it to a sphere, a ball, right? He's associating it to the Earth. That's
Yeah.
the difference. Whereas we think of reality as having the straight lines in.
yes, but on their model, you are always on the top of this ball or whatever. So you are always on the top.
Yeah, so you just go up. Crazy. But obviously, this was the one that led to the shorter than a straight line. I could call it a bit of a mental break, but you can hear it in his voice, right? You can hear the problems that he's trying to project onto other people, and they're Bob's problems, like misunderstanding what a straight line is, because in all of that, Bob didn't actually refer to an actual straight line. He just kept imagining that curves are straight if you look at it from a different position. He didn't mention that the surface level at the beginning was an actual straight line.
Yeah. Didn't he tell Rakia that he chopped off, was it 100 miles? Distance between 2 points, straight line. He chopped off 100 miles. The distance, I think, was 400 miles, and he chopped off 100 miles because he took a great circle route.
Yeah, he drove it over the mountains and everything, yeah.
Mm-hmm.
So
And then when I asked him about it, I think a week later, he gave me a greater distance, 6,000 miles, straight line, and he chopped off about 1,000 miles. He chopped off 1,000 miles from a straight line, 2 points. Yeah. Fantasyland.
yeah, we're talking about maps, and they're talking about these, you know, fantasy projections. Whereas we're actually, when I talk of a map, I talk of a map that's been measured 1-to-1 and then translated into a scale. You know, that you can read the actual maps. I don't know whether we have the same concept of what a map is.
I mean, like the ones you used to buy at the garage station many moons ago before GPS and unfold it?
Yep.
Yep.
Traditional maps. When I hear of map, that's what I hear, or that's what I visualize. There you go. There's the projections.
Oh yeah, this one's good with all the different ones. Yeah. Check that out.
So that's how many different.
There's the heart-shaped one. Yeah, that's my favorite one. Unbelievable.
I think that means, it doesn't mean anything to me, that at all. I heard Blue did a video. I don't know why he's having a go at Dell. I think they want to get involved with the floaty Earth, is it? I think is it Dell's got think
upward
I
movement.
yeah, I think at least I heard that Nathan Oakley had done a video about Dell and the up Earth, and I think I heard today that Blue Marble was having a go at Dell's mate, and he's got the floaty Earth, the mystery of the floaty Earth. So perhaps he wants to challenge Dell and the up Earth with the floaty Earth.
Oh, I think Betty has it taped in that department.
Yeah, but I think Blue's having a go.
In the center thing?
He's having a
Things
go at
float
Dell's
as a
mate, isn't he?
center? Yeah. I don't know. I don't know if he is.
Yeah, I'm pretty sure I seen Blue put a video out today. Gonna go at Dell's mate.
I don't know. I wouldn't want to take that on that argument myself, but I guess if he wants to take it on.
Yeah. Is that right, Blue? He's in the chat. Are you
Blue upward acceleration?
Yeah,
Come on,
no,
serious?
floaty. No, I think
the floaty one.
Yeah, he
the
wants
floaty.
to go against Dell and the upward, I think.
Oh, okay. I got it now. Okay.
The mystery of the floating Earth. I always thought that was Betty's idea, was to get in on that. It's a hot topic at the minute.
Wait until people hear the details of that one. Holy cow.
There you go. Look at that. I didn't know that guy's... Yeah, what's Dell's been doing to you, Blue? What's up with that? That's awful.
That dude looks familiar.
Oh, Dell was on Nathan's today. Did he go on it? That's Dell's mate. Gizmo.
Yeah. I think. I don't know. I've seen him somewhere. I can't place him.
He's the guy that caught the water bottle when Dell was dropping it out of his window.
Oh, okay. Right.
I don't know what Blue's got wrong with him. Why, Blue, why are you having a go at Dell's mate? What's that about? I've not watched the video, but I don't normally watch videos. Blue Marbles having a go at people. You've not been slandering him as well, have you, Blue? There you go. Nathan tore a strip out of Dell. And muting him. Seems like Blue wants to have a go at him. Did he do it the same day? That'd be terrible. Well, if Dell wants to come round and have a chat about any of that, open to it again. Open for conversation. I always couldn't understand what he was going on about. And I don't know why everybody wants to have a go at each other, because it's a bit unclear as to what's going on. Blue Marble Science has a floaty Earth. The mystery of the floating Earth. Apparently Dell has up Earth. I don't know what anybody else's opinions are. Me, ep or hey. All I know is that plumb bobs and levels need to be stationary in order to work correctly.
Well, some people think angles prove shapes. So
Yeah. Yeah, I mean, that's 2023. The state of science. So, like, taking it back to the old days, science is just the acquisition of knowledge. Yeah, it seems to have applied to fantastic knowledge. People are able to, like you say, derive shapes of things from measuring angles. People, what was Betty's argument? That things,
fall to the center.
yeah, things that always fall to the center. So if things have a center, therefore they do not
They float.
fall. Yeah.
Yeah, exactly. Yeah, that's his argument, more or less.
And if this is right, that Nathan's had a go at Dell, and on the same day, Blue Marble's having a go at Dell's mate. And,
Well, this is way worse than like Earth moving one way. This is way worse than that. This is saying things have centers, therefore they float. It's like,
They should.
wow.
So, for example, water droplets will never fall to Earth because it will drop to itself. Drops have a center, obviously.
A lot of people are saying a lot of silly stuff lately. I don't know what's going on.
I'm keen to know why Blue's slandering. Like, why is Dell's mate got a voice bubble saying that they're slandering him? Who's slandering him? Blue? I want to have to watch a video of Blue's where he's talking about people slandering people. I don't get it. Nah, he won't be listening now anyway, Blue Marble Science. If Dell's mate wants to come and have a chat and wonder why Blue's making a video of him, I don't know. Maybe, does he say that level's horizontal? I don't know.
Well, that's a tough one for them. They've been struggling with that one lately. Really bad.
Well, yeah, I think Betty's due to bring back the 1 degree over 69 miles. Because, like we say, that 69 miles is a straight line. Isn't it? Bob. Blue. 69 miles is a straight line. What say everybody here? If I say to you 69 miles, is that a straight line? Distance from A to B, 69 miles.
The shortest distance would definitely be a straight line.
But this is distance. This is not necessarily path, but just distance between 2 points. Always
straight line. Always. It doesn't tell you how long it takes you on the road, right? It's not the distance driving. It's the distance is just the 69 miles. That's a straight line.
And any deviation from that straight line adds to the 69 miles.
Yeah.
No way about that. No way around that.
Yeah. And that's one of the major problems that we had was when I was trying to explain to somebody the 1 degree over 69 miles. Somebody asked me for my example of how does that work. Well, it's just a 69 miles straight line, horizontal, because they're at the same elevation each point, and then the angle at each end is a 1 degree difference. If that's the difference, 69 miles, there's a 1 degree difference in angle over that 69 miles. So an
Yes.
angle measured would be different by 1 degree over 69 miles.
Yes, to the star, and it means that you have to have straight lines. So it has to be measured or calculated. No, measured, because you are measuring angle. So that would be measured angle between two straight lines. So you cannot have curve involved in that, because supposedly you are using trigonometry. So you have to have straight lines. Sorry.
I want to know what who's doing with the picture of Dell's mate. Can't get over it. Why you want to get involved, Blue? I think it's a bit ridiculous, but I mean, it's the latest thing, isn't it? This hot ticket, things falling. Blue Marble should be getting involved with it, really. Shouldn't be dealing with the straight line thing. The geometrics thing should have finished.
Take cover. Things are falling. Take cover.
Things are
Thank
falling.
God no things are falling here. Well, with the exception, one of those helicopters will fall, or a leaf from here and there, from time to time. But besides that, nothing else is falling. I don't see anything falling.
I put this Betty's side rule in again, just so everybody knows there are no sides. This is half of the problem of this model affliction. If you pick a side, then inevitably you will end up playing part of Betty's side rule. That's the reason there are sides built up, so that therefore you can have a false dichotomy. If don't pick a side and then be that other side, be the one that doesn't have a side, breaking the false dichotomy, right? Showing the false dichotomy.
Dare to go your own way. Dare to forge your own path.
Ask
Think for
questions
yourself.
of both people. I ask questions of
Yeah.
everyone.
Oh, yeah.
Nobody's really going to be able to give you an answer, because you're going to have to work it out for yourself. You can only ask people questions to help you come to your own answers for whatever it is that you have questions for. There are lots of people that we are going over. There's a video. There's a Plato play that's about the Sophist, and there's so much within that play, that dialogue, that explains why we're in the position we are today. There is an overall idea that we're in a conflict with each other, but I don't think we are. I don't think there should be a conflict. It should be people trying to just talk to each other. So many times people have want to cause conflict, and that stops the learning. It also stops the learning if you already assume that you know everything. If you base whatever you go off on assumption, then be ready to be challenged upon those assumptions. Don't just go back to your assumptions. Like, I think, who was it? Matthew Learns. Everything was based upon assumptions, and they were his assumptions. I'd love to know why Blue Marble wants to have a go to Dell making videos. Who told
Everyone's in a
him to do
fighting
that?
spirit.
Yeah.
Fight, fight, fight. Why can't we all just get along?
Who's told Blue to put a picture of Dell on? Come on, somebody own up. Somebody said, that'll be a great idea, Blue. Put that picture of Dell's mate on. Right, I don't know what else we've got. That was just a quick one I was going to go over with Bob. Anybody got anything else? What the Model Affliction Monday? Any other topics that we've got on the go?
Woo! You want an affliction of a model? I'll give you one. First, I'll ask a question. Obviously, it's a rhetorical question, but it has to be asked. Can the child be older than the mother that gave birth to it? The answer is no,
not.
right?
Yeah, obviously not.
Yeah, yeah. Okay, so since you said model afflicted, well, the shadow giants announced that they found a star that is 14.3, I believe, billion years old. But there's only one problem. Our universe, they say, is 13.7 billion years old.
Sorry, they measured time of a light.
Yeah. Time of a light.
I don't believe
Yeah.
you.
I don't believe it either. You said the model affliction,
Yeah.
right?
Yeah, but how do you imagine a method for this? Like
No chance.
age.
I don't imagine it because I can't imagine it. No.
It is based on assumptions. So
yeah, but that's part of the idea of this, the absurdity of something, right? So you say that they say that they've measured the age of a light. Well, that even within the concept of saying that, it sounds ridiculous. Like
That's why I say
can't
it.
even comprehend what it is that they're talking about.
Yeah, yeah. That's why it has to be said and repeated, so the normal people, can hear this, to hear what these so-called professionals are claiming. No normal person would believe that the child is indeed older than the mother. They would look at you like you were insane, right? Yeah. But this is what they said they found out there, yeah, in the model.
they found the star which is older than whole universe, right?
Correct. Yeah. Now, that's what they say. I'm not saying that I believe it for a moment. Since it's Model Affliction Monday, yeah, there it is. This, and I can even tell you another better one if you want.
Yeah, go
on. Well, you know those 6 baby galaxies they found that are too large and too far back in the model, and after the Big Bang, like a mere 500 million years old, which it should have taken them 13.7 billion to reach the size of ours, and some of them even surpassed it. So in other words, they found galaxies that were way too big for the time period. So latest solution, I read it a couple of days ago, professor in the University of University of Ottawa. Well, what he did was, to solve the problem, he just doubled the age and size of the universe. So in other words, from 13.7, he made it to 27 billion. Yeah.
How easy to solve that kind of problems?
Yeah, and it doesn't solve it though. I don't want to go into too many details, but yeah, it doesn't solve the problem. Let's just put it that way.
So the story can go on.
So the story can go on, yeah, but it doesn't work because I'll briefly explain it. Briefly. They're gonna have to come up with 2 different time periods. In other words, a woman, it takes 9 months for pregnancy. They're gonna have to split the fantasy in half and have way faster, like a baby coming out in like 3 months, right? And then having normal again back to 9 months type of deal. Like, to make a long story short, they're gonna have to come up with these crazy time frames. Yeah.
That sounds crazy for me.
Yeah, this is the latest stuff coming out from the shadow giants. The James Webb Space Telescope, this is it. This is what they're doing. This is where all the rave is now, and all the scientists are saying, well, not all of them, a lot of them are saying, and this doesn't look good. We might have to rewrite cosmology. But the people here in the discords are saying, "Oh no, you're crazy." No, no one's saying that. Everything is good. Don't look here. Yeah.
Blue marble. Remember, never applaud the other side. So that's what happens when people, especially blue marble scientists, when they depict sides, because blue marble science has obviously got you pegged as a on the level team member, SE. So it doesn't even matter what you say, especially when even when you're talking about the new developments within the blue marble science model.
Yeah. This is by no means definitive, Blue. This is new stuff. And guess what, Blue? I'm going to tell you your favorite word now. It has to go through peer review. Peer review, Blue. And if it passes, if all the magicians say yes, then you're going to have to come here and tell me, ASC, you know what? You're right. It's 27 billion years now. That's what you're going to have to do, Blue. Remember my words if this passes peer review. Yep.
Measure time of lights in the sky. Right. Do you guys see the the video I've put on. Again, this is another one of those videos where if you want to watch, you're going to have to come into the Discord, because this one, although you might have seen a few of the clips within the You Don't Understand. Let me see if I can get this. This is Rumpus talking about this particular video. Oh, because he when they had over there at the Blue Marble Science thing the other day. What was it called? When they were doing their science by the dictionary. This is Rumpus, so I'll play this.
Have you seen this? Have you seen the scary Open University program about non-Euclidean geometry?
Scary.
I can't remember now. Yeah,
Dev has actually got clips of it. He occasionally puts into his videos, and it's got the bearded guy showing you this, and trying to understand that Open University program. I've seen it about 3 times, and it's still, I can't quite get it right. I still can't fully understand what they're saying.
Is this something from the 70s by any chance?
Yes, it is.
Okay, so Rumpus has watched this 3 times. And he still doesn't understand it. So obviously, this is one of those things that you can go over quite a few times. Now, at the beginning of the journey, somebody once said to me that non-Euclidean geometry was the reason that a straight line wasn't straight, or that I didn't understand straight. It's very complicated, and it's all based around this whether you actually understand something that somebody says to you, or whether you can comprehend it. This is one of the big tricks to me whenever I sort out for me to try and make find an understanding of what was going on. This is one of the first videos that I found. Now, I think that Logos hands me certain things in certain orders so I can fully understand what's going on. You will be able to hear it. And I don't know whether I can get a link for it, because I don't know where it is. Right, so here we go. Listen to this. Now, this is something that can't really be understood. Because this is the concept of geometry. First off, you have to understand Euclidean, but that can come from hearing the ridiculousness of this. So here we go.
Geometry, the study of space, might seem to be the best understood of all mathematical subjects. Surely its foundations are the most secure. But when mathematicians in the 18th and 19th centuries looked hard at these foundations, they found things were not so comforting. Perhaps Euclidean geometry could be wrong. What if alternative geometries could be found? Could the nature of space itself be in doubt?
So they've got 18th and 19th century, when people looked at geometry, they just sort of went, possibly could be different. I don't know who these people were, but you've got to think back that around the 18th, 19th century, there was some sort of shadow giant where people wondered about space. But the space meaning 3D space that's around you. Euclidean. So this is non-Euclidean geometry and the foundings of it.
The way I have taken seems not to lead to the goal, but much rather to make the truth of geometry doubtful.
It's a strange phrase, the truth of geometry. What Gauss was interested in, when he wrote those words in 1799, was the deceptively simple question, is Euclidean geometry true? Does it correctly describe the space we live in?
Does Euclidean geometry... These are questions, right? It's more philosophical at this point. Is the space that we live in Euclidean? is it true? These are questions for all sorts of people to have a go at.
The answer might seem to be a simple yes.
Yes.
It does seem rather plausible that Euclid's geometry is true, doesn't it? But Gauss wasn't satisfied with what appears to be true.
I come more and more to the opinion that the truth of our geometry cannot be proved. Perhaps in another life we will get another insight into the nature of space which is unattainable to us now. But until then, we must not rank geometry with arithmetic, whose truth is a matter of logic, but rather with mechanics.
Okay. Anybody have an idea of that? At Gauss saying the truth of the geometry can't be compared with arithmetic because arithmetic is logic. Well, geometry is entirely logical too.
Yeah. They are the same things. Both logic. Arithmetics is logic and geometry is logic and harmony or music is logic and whatever you pick up.
Yeah. I mean,
Any
can
science.
you imagine the point that Gauss must have got to? Remember, just after Bacon and all of that sort of stuff.
Yes, he was talking about afterlife. That he would be maybe enlightened by something after life, because in this life we cannot have supposedly anything better. So I don't know what he's getting to, but strange words.
Well, yeah.
To understand how Gauss could doubt the truth of geometry, let's look a little more carefully at what it means to believe the Euclidean geometry is necessarily true. How could such a claim be proved? Well, there have to be some initial assumptions in order to get started. This is just what Euclid's 5 postulates are, statements we can't imagine being without. And then we'd want to reason from them to the rest of our beliefs about physical space. In that way, we would have shown that those beliefs are necessarily true, because they followed logically from our assumptions.
Right, okay.
No, I am not okay, because he's talking about belief, and proofs are not making people to believe. Supposedly they should make people to have certain knowledge, but he's talking about belief. I don't know why.
Yeah. Well, yeah, obviously you do. It's just this guy's scripted, right? He's a BBC character. He's just saying what he's told to say. So
yeah, I understand. Yeah, but still, it is not belief.
Yeah, if you base it upon an axiomatic system, then you go proof and build on proof, proof on top of proof, all the way, all based on the axiomatic system. And he calls them the postulates, but they're the axioms that you build your stuff off. So there we go. Listen.
But the difficulty that Gauss and other mathematicians recognized was not the method of reasoning, but one of these 5 postulates.
One of the 5 postulates. There are actually far more axioms. My book has 12 axioms and 3 postulates, so that's 15. He's talking about 5 here, so may necessarily not be telling you the entire picture in order for you to whittle down these. You have to get rid of the, obviously, no 2 straight lines can enclose a space, which is also one of the axioms, but not mentioned in here.
No one doubted that a line could be drawn between 2 points.
No one doubted a line can be drawn between 2 points. That's not in doubt.
Or that a circle could be drawn.
Or a circle.
But the 5th postulate wasn't quite so obvious.
Now it says this, the 5th postulate wasn't quite so obvious. We call it the triangle axiom because, yeah, it's dead obvious. A triangle has 180 degrees. To me, that's one of the most simplest ones. within this. But obviously the weakest link, because it sounds a little bit different. Listen to the excuse.
If, in a plane, a third line crosses two others, and if the sum of the angles alpha and beta is less than two right angles, then the lines will eventually meet.
On that side.
It was the necessity of having to assume this, the parallel postulate, that seems to have annoyed mathematicians down the centuries.
To having to assume that annoyed people. Why?
I don't know.
That's a strange claim, isn't it?
Yes, who? Maybe he can bring some names here. Who was triggered by that fact? Because, for example, I am not.
No, I'm not. It's perfectly sensible for that fact to have been made. To me.
It's not obviously true.
It is obviously true.
Why he's saying that?
It's because that's what he's scripted to say, right? This is, remember, when I first came in here and I was talking about a straight line and somebody said non-Euclidean, well, that's what we're dealing with here. It's the destruction of things that are obviously true. The advanced simplicity of it tells you that this is obviously true. That triangles have 180 degrees. Yet somebody wants to try and change that. They want to be able to bend a straight line. But you can't do it normally.
And when one is playing for such high stakes as obtaining certain knowledge of the world, it is worrying to have to assume a not quite obvious truth.
Did you hear that? One is playing for...
To have annoyed mathematicians down the centuries. It's not obviously true. And when one is playing for such high stakes as obtaining certain knowledge of the world...
When one... Listen to it again. High stakes.
To have annoyed mathematicians down the centuries. It's not obviously true. And when one is playing for such high stakes as obtaining certain knowledge of the world...
Certain knowledge of the world. Playing such high stakes. I mean, it is high stakes, right?
Yes, I'm not sure if is he supposing that people should turn to uncertain knowledge or what?
Well, they're not quite sure that Euclidean is certain knowledge, right? For some reason, they've decided that perhaps it might not be.
Okay, let's hear his reasons for that, because for me there are no reasons to doubt.
Yeah.
It is worrying to have to assume a not quite obvious truth. So people tried instead to prove it. That is to say, they discarded the postulate and tried to deduce it using just the remaining assumptions of Euclid. They make...
See, this is very strange to me. Just discard it and then try to deduce it using the other... But that's not how the axioms work, is it? I don't know. I don't get this method.
A sensible place from which to start. But trouble came when people tried to deduce theorems from this restricted list. The parallel postulate is really very useful, and it's hard to deduce theorems without it. People found a variety of assumptions that are equivalent to it. For instance, let's see what we can deduce about the angle sum of a triangle using the parallel postulate. If we assume the parallel postulate, then when we draw two parallel lines, these angles add up to 180 degrees. And so these two angles are equal. And likewise, for this line, these two angles are equal. Putting this information together, since alpha, beta, and gamma lie on a line, then alpha plus beta plus gamma is equal to 180 degrees.
Right, so that's the proof that triangles have 180 degrees.
Yeah.
Right?
Yeah.
It's a definite proof, right, that can be derived just because of the laws of geometry, right? But the laws of geometry rely upon this fact of parallel lines, right? Well, parallel lines are defined. They're not postulated. It's the triangle having 180 degrees that is axiomated within the axioms, surely. That's what the triangle axiom is all about. It's telling you on which side of the straight line the triangle will be formed. Very strange that, you know, that they're thinking that the development of this, I mean, that makes complete sense.
Two right angles. And conversely, by assuming that the sum of the angles is 180 degrees, we can deduce the parallel postulate. But be careful, that isn't what people were trying to do. They wanted to deduce the parallel postulate without making any other assumptions than these four.
Right, I don't understand that. It's just use a triangle to help deduce the parallel postulate, but not. Like he's saying that's not happy. They're not happy with that.
Yes, he's trying to say that you can. Some people are trying to deduce a parallel postulate without previous axioms. This is just insane. Because you have to, for example, you have to have defined straight line. If we are talking about parallel lines, we have to have defined what is straight line, because these lines being parallel have to be straight. So without definition of straight line, you cannot deduce parallel lines, because you don't know what straight line is.
No, parallel lines are defined already. That comes before the axioms and the postulates. Right? The definitions come before them and before these axioms and postulates. There is a definition that says parallel straight lines are such as that in a plane they do not meet.
Yeah, so you have to have some assumptions.
Well, the parallel lines are already defined. So what they're saying is that the axiom that states which side of this line the triangle will be formed, there is one position where the triangle isn't formed. And that's when the right angles are equal on both sides. You've got perpendiculars. And that's the problem. Just that position, one position, where there is no triangle formed on either side of the line. Right, that's literally what this triangle axiom states, that the side with less than two right angles. Well, if those two lines are both perpendicular, then both sides will have two right angles. And therefore there will be no triangle formed. And that seems to be the problem.
Not for me.
No, not for me either. But, you know, like, it's not a parallel postulate. It's a triangle axiom that tells you where the triangle's formed. And there happens to be one position where there is no triangle formed, and that's the problem for these guys. For some reason, I don't know why.
We can deduce the parallel postulate.
Here we go, listen.
But be careful, that isn't what people were trying to do. They wanted to deduce the parallel postulate without making any other assumptions than these four.
Than those four. Straight line being extended, circle, and all right angles being equal. But you can deduce it from those. Two straight lines where all the right angles are equal will not, it will be on both sides of the line. So therefore, no triangle will be formed. I don't get it. To me, it just sounds crazy.
For me, this is obvious because when he has this right angle, you can duplicate this perpendicular line in different position, and if you are duplicating the angle, you will know that these lines are parallel and they will not create triangle. So
on either side of the line. And if you change the angle on one side to make it less than two right angles, then the triangle will be there and not on the other side. Very simple, but obviously somebody's got a problem with it. I don't know why they have a problem with it, personally.
They didn't want to make another assumption, even one as plausible as this one, about the angles in a triangle. In 1733, an Italian...
They didn't even want to make an assumption of the triangle having 180 degrees, even though, well, it's mathematics, isn't it?
Italian, Girolamo Saccheri, had pioneered the most fruitful way forward. It was his idea to consider what a geometry could be like that was different from Euclid's. He hoped to show that such a geometry could not exist. Evidently, if Euclid's is the only self-consistent geometry, it must be the true one. Saccheri in fact found that there were just two other geometries to consider. In both these geometries, Saccheri accepted the first four postulates of Euclid, but used alternatives for the fifth postulate. His first geometry was one in which there are no parallel lines.
Right, so there are no parallel lines. This is a geometry that he's just invented. They've got rid of the triangle axiom and he's replacing it with this.
So any straight line through this point must meet this line somewhere along it. Now, if you're having difficulty imagining a geometry with no parallel lines, here's an example.
Right, you want to have a go?
Yes, I have difficulty to imagine non-Euclidean geometry.
Where do you think he's going to go? Right, because he's going to go demonstrating. Look.
On the surface of this sphere, we can imagine the straight lines as being great circles.
See?
Yeah.
Just imagine it. Like, we can imagine it, right?
Now let's consider a straight line.
Go on.
But still, on the previous picture, he was showing a real straight line.
Yeah.
Not curved line.
Yeah, you can see it in his face. He looks a bit.
So now he is talking about curved lines, and he's saying that we cannot have parallel straight lines because now curved lines he named straight lines.
You can imagine, yeah.
Yeah, you can imagine. I still cannot imagine. Sorry.
No, I can't imagine them being straight lines.
Parallel to this one, but through this point on the equator.
So can you see this?
Yes,
this
the
is
same
exactly
trick.
Right. No two straight lines can enclose a space. That's one of the axioms that they've got rid of when they say there's only 5 postulates. There isn't. There's other axioms that are already within the geometry that they're just trying to discard. And if you listen to what he's saying here, like I think this was it, right, for me. This part here now when he says this.
Here's an example. On the surface of this sphere, we can imagine the straight lines as being great circles. Now let's consider a straight line parallel to this one, but through this point on the equator. The angles at these 2 points on the equator add up to 180 degrees. But as I move up the globe, the lines get closer and closer together and eventually meet at the pole.
There you go.
So he's, or I would say that Bob, the science guy, is doing the same what he is doing. This guy
Exactly.
here.
Yeah. Just imagining that these are parallel. He said these are parallel, that they meet.
And whatever line I draw through this point, it must eventually meet this one somewhere. So there are no parallel lines here. There's an entire geometry associated with the surface of a sphere called spherical geometry, and it was well known in the 18th century. We can even have triangles on the sphere, where each side is an arc of a great circle. But spherical geometry requires a different set of postulates from those of Euclid's geometry, so spherical geometry isn't a candidate for Saccari's first alternative.
Right? Different postulates than Euclid's. Not that.
Okay, so,
Right, so he sort of had that. If he wants an example of it, but not that. Not that. He's saying.
So is he going to show us these new postulates and axioms?
No, we're dismissing it now. We're going into something else. That's that gone, I think, for a bit.
But perhaps it's conceivable that something else could be devised. Well, it wasn't to be. Saccari was able to show that the combination of Euclid's first 4 postulates and this property is untenable.
The property of none.
Untenable.
They're
Oh.
untenable. That's what he said, right? It wasn't to be that untenable. And it's known, but not. Right? So whatever he just said then, untenable.
Yes, undefendable.
Yeah.
So you cannot have that.
That's a bit of an upset, I bet, for anybody that wants to get into non-Euclidean to actually hear that said. It may be why Rumpus has problems with it.
Yes,
Because-
untenable spherical geometry,
Yeah.
undefendable, and generally not science.
So he's gonna stop now, I imagine. He's
Oh,
not
no,
gonna
no.
go any further, right?
No.
Oh,
Uh,
even after he says it's attainable, he's gonna continue?
Yeah, because that's spherical, right? Just dismiss
Oh.
that. That's like, that's not non-Euclidean. Mainly because it needs the sphere, and the sphere is Euclidean, so that's why it's not a real, true geometry, like they say. But it does get stranger
It
from
does lead
here
to
on
a
in.
contradiction. His second geometry was one in which there are many straight lines through P that never meet this line.
Right?
Those are straight lines?
There are
Wait a
No,
minute.
they are curved.
Yeah, no. Listen to what he says, right? Because this is another one of the eye-opening moments.
To show the results of geometries like this, my straight lines will appear curved, so the pictures will look rather odd. But this second geometry proved to be much more obstinate.
Did you hear that?
This is ridiculous,
He
man.
just said. Watch, listen.
His second geometry was one in which there are many straight lines through P that never meet this line. To show the results of geometries like this, my straight lines will appear curved, so the pictures will look rather odd.
That's it. No other reference to it, right? He has to draw curved lines to show it, but there
And he
are
points to the
many.
straight line.
There are many
Yeah.
other that, but he has to show them as curved, so it might look a bit ridiculous. So That's it. That's the best you're gonna get. You just have to accept it looking ridiculous.
Okay, but still, at the bottom we have still straight line.
Yeah.
So
Yeah,
why
but these
he's
other ones aren't straight, right?
Yes, but he's saying that they will be no parallel, or
Many,
because they are
there
not
are,
straight.
No, there will
Many.
be many straight lines that are
But
parallel
he's
to it.
showing not straight lines. He's
Exactly.
showing
But
curved
they're all
lines.
going to be crooked.
There's
Yeah.
no way to actually have the straight line that is many that are parallel to a straight line. It's impossible. But he's imagining this geometry, right? This is a nutsacking, literally. This is why you shouldn't really do it. And it's going to go and explain it in a minute.
But this second geometry proved to be much more obstinate.
Much more obstinate. Much more obstinate, I'd say, because, I mean, look at it.
Simply would not go away. As the Swiss mathematician Johann Lambert wrote in 1770,
I have sought such consequences of this hypothesis to see if it did not contradict itself. From them all, I saw that this hypothesis would not destroy itself at all easily.
this is
You're kidding me, right?
Contradict itself. It wouldn't contradict itself. Because it's a fantasy. You've got to imagine they're not that to start off with. And then you've got to find why it won't contradict itself. But you've imagined they're not that. It's part of your axioms, your postulates. You've placed it in there. And then now you're asking the not that to contradict itself.
came in. He read Lambert's book when he first went to Göttingen in 1795, and he shared with his predecessor the belief that if only this alternative hypothesis could be made to contradict itself, then at last Euclid's geometry would have been shown to be true. But as Lambert discovered, this assumption may produce strange theorems, but there does not seem to be a contradiction.
It might strange theorems, but there's no contradiction. It's just telling you that there's a study needed to be done within contradiction. Whereas I think there's already a contradiction there.
Okay, but
go on.
From what he said, it means that if he is creating this strange theorem, it means nonsense.
Mm-hmm.
And on other hand, you have a sensical theorem. They are in contradiction that one is sensical and one is nonsensical. But I would say that there is still contradiction there. But
well, what they're doing is they're trying to make a new geometry and then trying to make it contradict itself. Whereas they're not applying that to Euclid. They're not saying, well, let's just make Euclid contradict itself and then we can prove it's not true. They've already got Euclid that doesn't contradict itself. It's a perfect axiomatic system all the way through from beginning to end with zero contradiction. Otherwise, it would already be exploded logic. So they've set up a scenario where they've made something that he's having to draw curved lines because he can't express it as a straight line. Even though he's saying there are many straight lines that are parallel to it. But it's impossible to show it. And he can't find a contradiction within it. I'd say the contradiction of you not being able to represent it is it's a contradiction. But,
yeah, because in Euclid you can represent what you think.
Mm-hmm.
By drawing straight line, if you are thinking about straight line, etc. So, and he is drawing a curved line and imagining that they are straight. This is just nonsense.
Yeah. Right, here we go.
For example, in this geometry, the angle sum of a triangle is always less than 180 degrees or 2 right angles, and figures cannot have the same shape without also having the same size. Unexpected, but not logically impossible. Gradually, Gauss came to believe that perhaps this alternative geometry might be logically consistent. But although Gauss corresponds...
It might be logically consistent. It's just
just a possibility.
Yeah, it might
just
be.
Possibility. This is modern science. If there is some grade of possibility, we can go with that.
Yeah, it's worth looking
No
into.
certain knowledge.
With those who were working on the matter, he did little to develop their ideas. To follow those who really did investigate a new geometry, we must turn to the distant corners of Europe, to Russia and to Hungary.
Right. Now these guys, you need to listen to this specifically, because if you want to hear what the nutsacking is, this is where it comes from.
Gauss's old student friend, Wolfgang Bolyai, had gone back to Hungary and become a professor there. His son, János, turned out to be a mathematical prodigy and learned of the problem of the truth of geometry from his father.
Right, can you remember this from the You Don't Understand video? He comes down and he changes colour and there's the triangles behind him. It's been there all the time. And listen to what these guys say.
I entreat you to leave the science of parallels alone. I thought I would sacrifice myself for the sake of truth. I was ready to become a martyr who would remove the flaw from geometry and return it purified to mankind. I turned back when I saw that no man can reach the bottom of this night.
Do you want to hear that again? Do you want to hear that again?
So he was trying hard but failed, and he had to return to normal.
He wanted to be a martyr, right? To sacrifice himself. He knows the troubles, what you have to do to your mind in order to go to these places. This guy knew. Listen.
Hungary and become a professor there. His son, János, turned out to be a mathematical prodigy and learned of the problem of the truth of geometry from his father.
I entreat you to leave the science of parallels alone. I thought I would sacrifice myself for the sake of truth. I was ready to become a martyr who would remove the flaw from geometry and return it purified to mankind. I turned back when I saw that no man can reach the bottom of this night.
He's talking to his son. Don't,
Did you hear him say?
Do this.
Yeah.
Did you hear him say right at the first of it though? He says
that's the one. Yeah.
The problem of the truth of geometry.
Yeah.
Yep.
Think about that statement.
That's it. That's exactly it.
So for them, the problem was that geometry, Euclidean geometry, is telling the truth.
Yeah, it's
so
a
you cannot deceive. You cannot deceive people by Euclidean geometry.
Yeah, and
that's their problem.
Yeah.
Yeah, and specifically parallels. He said.
Mm-hmm.
That's the nutsacking right there.
Yeah, this is the problem. This parallels, but the parallels proof straight lines. It's the perpendicularity that shows that two lines perpendicular to one line. This within this one postulate, or they call it postulate. I say the triangle axiom. It's summed up so easily with the triangle formed on either side of the line. One position where the triangle, no triangle's formed. Simple, really. The formulation of a square, rectangles, all same thing. Based around this, right? So one guy is telling his son, don't do it. I had to go to the brink and I had to turn around and come back again.
What a statement.
Didn't listen, and his father tried again.
Listen.
I have travelled past all reefs of this infernal Dead Sea, and have always come back with broken mast and torn sail.
Holy shit.
He's troubled, right? This
Trouble?
is, yeah. Going and sitting at the end of your garden looking at the lights in the sky after this sort of stuff, aren't you?
Damn.
That's a guy talking to his son about matters of the mind, right? Because that's what this is. It's
This
way
is
more,
good, bro.
way more than anything, right? That you'd
Who are
imagine
you,
about
of course.
geometry.
Who are you going to be more sincere to than your son? Right? This is like amazing.
Right, so let's go.
Imagine his consternation when his son replied in 1823,
I have not yet made the discovery, but the path which I have followed is almost certain to lead me to the goal, provided the goal is possible. All that I can say now is that I have created a new and different world out of nothing. All that I have sent you thus far is like a house of cards compared to a tower.
Do you want to hear
So
that again?
so Sam said, no, I am the
House
God.
of cards.
I am God because I can create from nothing. He said
Yeah,
that.
I could create a world from nothing. Like he's just fantasizing.
This is truly unbelievable.
That's his son's got nut sacked. It's like, don't tell me what not to do, Dad. Watch this. Like, so let's listen to these conversations, because this is when you listen to these two. This is Janosch and Bulliai.
Hungary, and become a professor there. His son, Janosch, turned out to be a mathematical prodigy and learned of the problem of the truth of geometry from his father.
I entreat you to leave the science of parallels alone.
He learned from it, right, from his dad. His dad went, don't do it, right?
Yep. Stay away, son.
Yeah, this'll trouble your mind. Keep away from it.
I thought I would sacrifice myself for the sake of truth. I was ready to become a martyr who would remove the flaw from geometry and return it purified to mankind. I turned back when I saw that no man can reach the bottom of this night.
The son didn't listen, and his father tried again.
I have travelled past all reefs of this infernal Dead Sea, and have always come back with broken mast and torn sail.
That part, man.
Classic.
That's like British, like poetry, like.
I was thinking of putting this into a You Don't Understand song.
Oh,
These clips, because they are good. They are good.
The mast, the one with the broken mast in C, yeah.
I have not yet made the discovery, but the path which I have followed is almost certain to lead me to the goal, provided the goal is possible. All that I can say now is that I have created a new and different world out of nothing. All that I have sent you thus far is like a house of cards compared to a tower.
Right, so he said, like, the path he was on was certain to give him it, provided it was possible. But he's created a world from nothing. So he's literally gone into his mind, created a world from nothing, and he's certain it's there if it's possible. That's broken mind, right?
Totally.
That's mental case. Already.
Yeah.
And he's also telling his son that he's giving him a broken fantasy.
Yeah, well, he said don't try it, right? He didn't express how bad it is because it's in the mind. This isn't like a journey that's going to be hard and you're going to get blisters on your feet or shit like that. This is your mind that's at stake. This is madness. And that's where his son's gone. In the reply is, I've created a world from nothing. and I'm going to do it. I'm going to fix the flaw in geometry. But what flaw? It's perfect. Euclidean geometry is perfect already. There is no flaw.
He wants to curve the floor, I think. Is that a way of him saying that? I don't know, man. He's ruined.
People are leading other people into this, right? Somebody's encouraging them to do whatever, right? Gauss is sat at the sidelines. It's mad.
In the two phrases, I have not yet made the discovery, and I have created a new world out of nothing, lies the whole story of what we can begin to call non-Euclidean geometry. For once a new geometry can be conceived, it is possible that this geometry is the true one. To determine the truth of geometry would henceforth be a task for the experimenter, and geometry would be like mechanics.
Did you get that?
Yeah.
Literally. I'll rewind it, because this is the bit after Janosch.
Provided the goal is possible. All that I can say now is that I have created a new and different world out of nothing. All that I have sent you thus far is like a house of cards compared to a tower.
Right, so listen to that. He's obviously troubled. We've gone over that. Listen to this.
In the two phrases, I have not yet made the discovery, and I have created a new world out of nothing, lies the whole story of what we can begin to call non-Euclidean geometry. For once a new geometry can be conceived, it is possible that this geometry is the true one.
Once a new geometry can be conceived, it's possible that this geometry can be the true one.
Yeah.
All
bring
you
it
need
into
to do is conceive it.
Yeah.
And then they're going to go, well, it might be possible that that's the true one, because there's something up with Euclidean, apparently. Right?
Yeah.
How can we be sure that Euclidean geometry is the true geometry? And then let's get mad people to imagine, make new worlds out of nothing, and then go, well, that might be the true one then. That's madness.
Literally madness. Yeah.
Now, can you understand why Rumpus? Because Rumpus has to go with this. If you put your faith in mathematics, and this is the sort of stuff, this non-Euclidean, that you have to place yourself in, then this sort of has to become a must. Like, how many people have told us about non-Euclidean geometry? These people have gone to the brink, but modern day people are already there. They'll quite readily tell you that they can measure triangles with more than 180 degrees, which is not Euclidean, right? The triangles formed on either side of the side of the line with less than 2 right angles. Well, these guys want to make a triangle with more than 180 degrees, which would make it on both sides of the line. Wouldn't it?
Yeah.
That's where you're having the problem, right? Because if you go with Euclidean as being a true geometry, then to say anything other than that requires the triangle to be formed on both sides of the line. And then it wouldn't even be a triangle, because it'd be formed on both sides of the line. There's 4 points.
That would be a square or whatever.
Yeah.
Rhombus. Yeah.
It's sort of like, if you can't find, they're saying they can't find a contradiction in it. And it's like it's staring you right in the face. There's contradictions all over the place the moment you try and imagine they're not that. With mad people.
To determine the truth of geometry would henceforth be a task for the experimenter, and geometry would be like mechanics.
So the experimenter? The experimenter now has to go into the mind of Bulli, making a new world out of nothing, to experiment, to find I don't know. This is the way that they did it, though. This is, these guys.
But the discovery is not yet made for sure. There could still be a contradiction just around the corner. In 1831, suppressing their remaining doubts, they went ahead and published Janosch's work. It came out as an appendix to the father's book on geometry. A copy was sent to Gauss, who replied,
If I commence by saying that I'm unable to praise this work, you would certainly be surprised. But I cannot say otherwise. To praise it would be to praise myself. Indeed, the whole contents of the work, the path taken by your son, the results to which he is led, coincide almost entirely with my meditations.
Meditation.
Yeah.
Okay.
Gauss has gone, hey, don't worry, mate. I'm mad too. We've all been there, trying to solve this tricky little problem. It's when we know, we know what has to be, right? We know this dogmatic thing. We know how it has to go. And the problem is the straight line. You can see the problems within it. So can Gauss. Everyone can. You're having to break away from what is. Sorry, go on.
I was going to say, there's a quote from Bolliat and Lobachevsky. They say those geometries that they were conceiving, they had to keep them in 2D because if you went to 3D, it would show the contradictions.
Yeah. That they know
They
that
knew
there's
it.
contradictions, yeah. There's contradictions everywhere. It's fantastic how we've got this far through mathematics, where mathematics is entirely logical, but this is illogical.
Understandably, Janosch never forgave Gauss for what he saw as an attempt by the most famous mathematician of the day to claim priority falsely over a completely unknown mathematician. In Russia, quite independently, a similar story was unfolding. A professor, a mathematician at the University of Kazan, Nikolai Ivanovich Lobachevsky, was also trying to prove that there was a second, logically possible geometry. In 1829, he published the first description of a non-Euclidean geometry, 2 years before János Bolyai's publication. But there was no way that János Bolyai could have known of Lobachevsky's work. So what is it that these mathematicians had achieved? Since their descriptions of non-Euclidean geometry are so similar, it's convenient to describe their work together. And because their geometry turns out to be somewhat different from that of Euclid's, we have to suspend many of our conceptions of the world and prepare to enter a new universe.
Right.
What?
Yeah. Just conceptions of the universe, right? So now you're into what he's telling you. This is imaginometry, literally.
Yeah.
That's where we're going. Come with us on a journey. Let's go.
Perhaps the first surprise is that Lobachevsky and János Bolyai both began by describing a three-dimensional geometry. In this three-dimensional world, they assumed that a line and a point defined a plane, and that in such a plane there are always infinitely many lines through the point that do not meet the given line. They found that on this assumption there are two really interesting lines through the point. There is one in each direction that is asymptotic to the initial line.
So, like Buster says, this is 3D, but it's a point and a line. It's only 2D.
Yeah.
It's only 2D, but you've got to imagine it's 3D because he's just said 3D.
Yeah, because you cannot depict that. Because you can depict 3D in normal Euclidean system.
Yeah.
So, but this new mathematics cannot depict.
It's a 3D
in
slash 2D. You have to imagine it's 3D, but you're only ever going to see it in 2D. It's a different universe. And those lines that you see there, those multiple lines, they are straight.
We we worked this out ages ago. That it's a whole different set of rules, and everything has to stay within that universe, that conception. But what we deal with when people come in saying non-Euclidean geometry, they are interchanging them like it's no problem, and you can't do that.
Yeah, there's a difference between reality and what works in reality and this non-Euclidean. This is entirely conceptual, right? Those are straight lines that you can see there. Well, not straight lines, they're planes, supposedly. But you just have to imagine that they're straight. They're multiple different straights. Really, there's no curve. That's what they're doing. They're just multiple straights. They're calling curves straight, but then saying, well, listen, you'll have heard this.
That is, gets closer and closer to it, but never meets it. These lines we call the asymptotic parallels to the initial line, so that all these lines eventually meet the baseline, and all these lines eventually diverge from it in both directions.
Circles.
But it's these, the asymptotic parallels, that we'll be particularly interested in. They wanted to work out the trigonometry associated with this new geometry.
Right, so they've said there's loads of different lines, but there's just these two that they're interested in for some reason. I don't know why they're not bothered about any of the others. That makes no sense at all. And these ones, they're calling asymptotic parallels because they're obsessed with the parallels. They're obsessed with destroying parallels or trying to confuse people about parallels. I'm not too sure which way it goes. But you're in a fantasy land.
Sounds like they're starting up with like concept.
Bit breaky up there, Buster. Are you driving to or from work, perhaps? I didn't get
from.
Yeah, I didn't get it. No, too roboty, Buster, sorry. Right, here we go.
For example, they asked, given this distance, what is this angle?
See, look at that. It's got a right angle here. So it does have one that is actually a straight line. But these ones are straight lines as well. So even within this non-Euclidean, there is a straight line. And then a straight line. I don't get it. But hey, two different straight lines. But meant to be the same.
That was my objection against flat earth math, because I said that he's trying to use normal Euclidean straight line and this great circle and both of them are straight lines. So this guy is doing the same, or I would say that flat earth math is doing the same as this guy.
Yeah, you can't get rid of the concept of a Euclidean straight line, which is what's in here at the bottom. It's got a right angle with the the horizontal and the vertical.
So we have contradiction here.
Yeah, blatantly, but like internally consistent, they call it. But because you've took yourself out of Euclidean, and you've put yourself in a strange place. That's the only way you can do this, because like you say there's an obvious contradiction, but that's because you're within reality. But you're being put in reality because they do have a straight line and a right angle. It's mad.
Known as the angle of parallelism. And they wanted the answer as a function of the distance, a. And here's something relatively new.
Look, he's put pi in there as well.
Function of the distance.
Yeah. The angle
Strange.
is a function of distance. You've heard it recently, or
From Flat Earth Math, yes.
Yeah.
Because he said that this is the same angle, but it's different at different distances. So it is the same and different. So
yeah,
strange.
The use of functions to do geometry. But first, to orient ourselves, we'll turn this picture round. The initial line now becomes a perpendicular.
Right, now this is something I learned also. They have this idea where they had to have models of this, whatever it was that they were doing. They had to have a model for you to look at, imagine, for it to become mathematically true or whatever. And this is it. This is fantastic imaginometry. See whether you can get on with this.
Standing on this plane. And here's an asymptotic parallel to the line. Now, in this novel geometry, they picked another point.
Novel.
So they got a right-angled non-Euclidean triangle with its right angle here. And through this point, they drew the asymptotic parallel to the original perpendicular.
Right, so he's got a Euclidean triangle on a plane. A Euclidean plane.
Over at this vertex, they added a tiny little hemisphere. And between these three lines, on the surface of the sphere, they drew a tiny spherical triangle. Now for the wonderful idea. Remember the spherical geometry I showed you earlier? It doesn't depend on Euclid's postulates, or indeed on any assumption we make about parallel lines. So any trigonometric formulae describing the spherical triangle are true, even in this peculiar non-Euclidean world. Now, it turns out the shape...
Do you see that magic trick? Do you want to go over again? Do you want to hear it?
Yeah, I can see that trick. So this is projection of triangle, normal triangle, onto the sphere.
Mm-hmm.
This is just projection.
But it's an internal triangle. Which sphere are they projecting it on? He's got a Euclidean triangle on the base. He's just said, like, he said, remember the spherical geometry that we disregarded earlier?
Yes, so this is out.
This is magic trick.
Now for the wonderful idea.
Remember
the spherical geometry I showed you earlier? It doesn't depend on Euclid's postulates, or indeed on any assumption we make about parallel lines.
It doesn't depend on Euclid's postulates or any assumption about parallel lines.
He's lying.
Yeah.
So any trigonometric formulae describing the spherical triangle are true, even in this peculiar non-Euclidean world.
So they're true in the peculiar non-Euclidean world. He's just grabbed something and just said, in this new geometry, we're going to have this other geometry that's necessarily true within this. Very, very clever little trick. I mean, you could do things like that. Well,
now, it turns out the shape of one of these triangles determines the shape of the other. So if we know all about the shape of the spherical triangle, it should be possible to determine the shape of the non-Euclidean triangle.
It's a Euclidean triangle as he started off with it. Didn't he? Do you want me to go back? I'll go back if anybody can. But he started off with a Euclidean triangle.
Yes, so this is circular reasoning.
And now he's just made that little thing and said that there's a relationship between that and the non-Euclidean, and it's just changed.
Yeah, so this is stolen concept because the cause of this, let's say, spherical triangle, which is normal triangle, now it is effect of spherical triangle. So this is the trick.
Yeah.
That he's superposing what was the cause, now is conclusion. So this is circular reasoning and stolen concept. Because now he will say that the cause of normal triangle is spherical triangle. But before he said that the cause of spherical triangle is normal triangle. So for me, this is just a big lie.
It's more fantastic, this, so.
So Bolyai and Lobachevsky could assume the spherical trigonometrical formulae were true, and from them deduce what formulae would describe the triangle in the non-Euclidean plane. They found they were able to deduce all they wanted about the new geometry. For example, by treating the original figure as being one of a triangle with a vertex at infinity, their formulae tell you what this angle is as a function of this distance. And that's just what was required, for that gave them the angle of parallelism.
The angle of parallelism. That's fantastic, that, right?
Yeah.
That's
180 degree, like something like that. No.
There's a wonderful extra to be got out of this. In proving their results, they made use of this bowl-shaped surface, which meets every possible asymptotic parallel to the original perpendicular at right angles. Here and here. It turns out, oddly...
See, at right angles. What's that tell you? Like, they're curved. It's like, no, right angles. You're talking about a Euclidean right angle here?
Yeah, but because this is triangle projected on a sphere. So they think that they are still straight lines and still right angles. This is just madness for me, but okay.
Yeah, he said, like, in him saying right angle, that is an assumption of Euclidean 90 degrees. Perpendicularity. Right? Which that obviously isn't. So you've got to place your mind in a place to accept the non-Euclidean ability of this to be a right angle. Like, you've either got to swap your mind and your understanding of what you perceive a right angle to be in reality and swap it and place it there on that thing, or you imagine that that is a right angle and the Euclidean one is different somehow. This is why your mind goes messed up, because you have to imagine something different from being a right angle. But a right angle is two straight lines maximally opposed to each other. Like, you can't be anything other than that. But this is crazy.
enough that this triangle has an angle sum of 180 degrees exactly. And indeed, any triangle we draw on this surface has an angle sum of exactly 180 degrees. So within the strange three-dimensional non-Euclidean space of Bolyai and Lobachevsky, there is also an accurate picture of two-dimensional Euclidean geometry represented on this bowl.
So yeah, Euclidean geometry is within that bowl. They've literally placed Euclidean inverted on the inside. So, you know, when people imagine there's an elevation change of a horizontal, They're thinking of that bowl, aren't they?
Yes, and they are turning a two-dimensional figure, planar figure, into a spherical three-dimensional
But
figure.
it's internal to the sphere, not external.
Yeah,
That's
yeah,
the point
that's-
with this. And that's why people imagine this as being like upside down on the top. It's crazy. They literally exploded minds. I mean, look at it. The guy's holding it in his hands. This is your exploded mind. If you go down this route.
It would seem then that Bolyai and Lobachevsky had finally resolved the problem of the status of geometry. By exhibiting what Lobachevsky called an imaginary geometry different from Euclid's, surely they had shown that Euclidean geometry was not, after all, necessarily true. But by and large, the response to Lobachevsky and Bolyai's work was poor, and in a sense, we can see why. After all, they had both proceeded from an initial assumption about parallels. Strictly speaking, their work doesn't show that that assumption is logically possible. What was required was a complete rethink, something that could embrace both the old way of doing geometry and the new ideas. The man who was to provide this was a student of Gauss, the shy but gifted Bernhard Riemann. Riemann's arguments were to revolutionize the way in which geometry was perceived. He didn't start with the belief that we all know what Euclidean geometry is, or even with the view that we know what straight lines and angles are. Riemann argued forcefully that you could do geometry on any surface, such as this pear-shaped surface. He started instead with the idea that we know how to measure length. That's something, he said, you can do in any geometry. If we have a curve on the surface, then we use the calculus to measure its length. Riemann was also able to define what a straight line is in terms of length. The straight line between 2 points is just the curve of shortest length on the surface between the points. What probably most excited Gauss, who was very impressed by Riemann's ideas, was that this new idea of what geometry is put all geometries on a par. Euclidean geometry is just now one of many geometries, the geometry of a flat surface. And what precisely is a flat surface? To see that a surface is flat, we can just step off it and look. But if we want to do geometry in Riemann's sense, we have to do it using properties that lie solely within the surface. Well, it was Gauss himself who had shown how to define what's called the curvature of a surface, in such a way that it can be determined from properties within the surface alone. When we find, as we do, that for any triangle we can draw on this surface, the angles add up to 180 degrees, that amounts to showing in Gauss's language that the surface has zero curvature. In other words, it's flat.
There you go. So somebody was asking us that the other day, right? Gauss said that if you measure 180 degrees within a triangle, then you know you're using Euclidean geometry. Everyone all right with that?
Yeah, but still, if you have 3 points, you are creating a plane. So
yeah,
how
exactly.
How can you create a non-planar surface using 3 points? You have to already create curved lines.
Yeah,
So,
but you've got like you could have like 3 points at the top of mountains, right? And then you'd know what the space is by measuring the angles. Right? You can be sure that you are living in Euclidean 3 space by measuring the angles of a triangle to 180.
yes, that's obvious.
Yeah.
For me, this is just madness.
But if you get somebody who says that they measure more than 180 degrees, then, you know, like they're only obeying Gauss's rules, right? So you you'd know which geometry to use by measuring the angles of a triangle. Go back over that and play it again so people can hear it.
We can just step off it and look. But if we want to do geometry in Riemann's sense, we have to do it using properties that lie solely within the surface. Well, it was Gauss himself who had shown how to define what's called the curvature of a surface in such a way that it can be determined from properties within the surface alone. When we find, as we do, that for any triangle we can draw on this surface, the angles add up to 180 degrees, that amounts to showing in Gauss's language that the surface has zero curvature. In other words, it's flat. In the same way, if we find ourselves on a surface in which the angles of every triangle add up to more than 180 degrees, then we're on a surface which has positive curvature, such as this sphere. And here's a triangle on a surface we wish to understand. It's easy enough to construct a bit of such a surface, and we say it has negative curvature because it curves towards us in one direction, but away from us in the other. Well, what's worrying about this surface is that when you try to extend it, it might not be able to grow beyond a certain point. That would be dreadful for any surface that was trying to be a model of even two-dimensional space, because nobody believed that space came to an end.
See, so you've got one spherical that can't be the one, and then the other one that has less than, and yet there's problems with limits.
Yeah, because it has to end on the top. It will end at the top, and it will end at the bottom.
Yeah. Yeah, on an axis, like it's this one's based around the parabola, isn't it? And the the asymptotic parallels that go both ways, but they are limited to these, well, to the limits of the surface. It's tough, right? Because there's limits both ways. There's only really one that has no limit, and that's the plane.
The man who was able to overcome this dilemma was an Italian, Eugenio Beltrami. Beltrami's solution was ingenious.
What's this? It was ingenious.
Observed that an atlas is as good a description of a sphere as any, if you know how the scale varies from point to point. You can work out from the atlas how far apart these points are on the sphere. So an atlas is a perfectly good description of a surface of constant positive curvature. It has some disagreeable features. For example, on this one, equal distances on the sphere appear to stretch more and more as you move outwards.
Appear to stretch? They are stretching. Not appear. There is huge distortion.
Yeah.
Beltrami's idea was to construct an atlas for a surface of constant negative curvature. If he could construct such an atlas, then he could hope to show that there was such a surface, and that there was no problem about it stopping at a boundary. Beltrami did indeed succeed in constructing such a map.
I don't know whether you've ever seen this before. Anybody?
No.
Should be in here because this
will be crazy.
Watch
I bet.
this map, yeah.
But it's the version constructed by Henri Poincaré that I'd like to show you.
Poincaré.
Like the maps in the usual atlas of a globe, distances are distorted. In this case, the whole of two-dimensional non-Euclidean space is depicted inside this disk. As I
whole of non-Euclidean two-dimensional space is within that disk. And if you've never seen, well, have you seen the angels and the demons? Because this is what it's about. The limit, the boundary. What?
Move outwards, distances appear to shrink. But that's a distortion of the map-making process. We non-Euclideans don't actually shrink, nor do we ever run up against an edge.
We non-Euclideans, right? You just get smaller as you get to the outside.
Ingenious.
It's like a fractal.
Now, looking from above, we can see how on this map non-Euclidean straight lines appear as arcs of circles perpendicular to the boundary circle, or as diameters, but angles appear actual size. So you can see that in this triangle, the angle sum really is less than 180 degrees, or 2 right angles. And here, you can see that in non-Euclidean geometry, there really are 2 asymptotic parallels to this line through this point. Of course, the lines meet at the boundary, but that's a non-Euclidean analogue of the way we talk of Euclidean parallel lines meeting at infinity.
See? Non-Euclidean lines meeting at infinity. Who says that? Anyone else ever heard that?
Yes, but this diameter is still straight line. So why he's talking about non-Euclidean?
Oh no, that's only because you're looking at it from above. He did make that thingy at the beginning. You're looking at it from above.
So, maps like this disk indeed show that a surface of constant negative curvature exists. For the first time, mathematicians could be certain that an alternative geometry was possible. So now, not only could one doubt the truth of Euclidean geometry, one had to doubt it.
You had to doubt the truth of Euclidean geometry.
But still,
Like,
this
no.
table is flat. It is not. It has not negative surface. Sorry.
Is anyone being forced into the position of having to doubt Euclidean geometry? No, not me. It doesn't affect my understanding of Euclidean geometry. I know that this is imaginary. It's not real.
Yes, I would say that this program, because this is BBC program, okay, so it proves to me that in order to dismiss Euclidean geometry, you have to say load of bullshit. For me, that would be positive proof for Euclidean geometry.
Yeah, I think these words that they use.
So now, not only could one doubt the truth of Euclidean geometry, one had to doubt it.
Not only could you doubt it, you had to doubt it. Imagine coming into geometry lessons and hearing this. Like, you had to doubt it. This is Open University.
But what of three-dimensional space? Could a three-dimensional non-Euclidean universe be depicted? Well, here is such a model.
I see a ball, Euclidean ball.
On a plane, like split in the middle with another ball inside it. Right? It's a ball in a dome.
Yeah.
Completely ridiculous.
The whole of the non-Euclidean universe is inside this ball. Here in this slice,
the whole of the non-Euclidean, it's inside a ball. The entire universe is inside a ball.
Is our two-dimensional representation with the triangle that we saw earlier in the Lobachevsky model. You can see the asymptotic parallels, which now meet the original line at the top. The asymptotic parallels appear curved because of the way the map has been made. Again, this apparent point of contact is actually infinitely far away in our non-Euclidean space, as are all the points of this enclosing sphere.
So we cannot have this because you cannot have ball, because ball is undeveloped, undevelopable surface, so it has to have limit. But this asymptote has no limit. So this is just impossible.
It means yeah, but that's just how the map was made.
Okay, but this is literally impossible. What he just said is impossible. You cannot have this asymptote inside the ball because it cannot meet. this straight vertical line, these two asymptotes.
Yeah,
They
you're
he
thinking
said that.
Euclidean. You see, you're still thinking Euclidean. You've got to explode your mind and have something like completely the opposite of what you'd imagine. This is
No. I am saying that he's talking about this big ball. This big ball is inside. So being inside big ball means that you have limits, and the limit is this big ball. But he said that this asymptote is infinite. So it cannot meet inside this ball, because you cannot meet asymptote with this straight line within undevelopable surface. It is impossible.
I think it's a marvelous model. They should, you know, when everybody talks about non-Euclidean, they should, you know, be shown this to say like explain where your 2D is, because the 2D's are plain. And Euclideans within this.
And this sphere, inside the large one, is the surface which is perpendicular to all the possible asymptotic parallels to that first line. And on this surface, the angle...
That's perpendicular, right? That's a perpendicular surface within non-Euclidean. Yeah, doesn't somebody want perpendicular surfaces to look like that in Euclidean? Isn't that what we're taught? Or maybe we don't live in Euclidean anymore. I don't know. It's crazy, isn't it? But that's perpendicular. That's what he says. Listen, again.
Are all the points of this enclosing sphere. And this sphere, inside the large one, is the surface which is perpendicular to all the possible asymptotic parallels to that first line. And on this surface, the angle sum of any triangle is 180 degrees. So this three-dimensional atlas confirms that a three-dimensional non-Euclidean space is possible. It now does become a matter for the experimenter to determine which geometry is the true one. Finally, going back to this model, there are two equivalent ways of thinking of this configuration.
He said the experimenter. Over to the experimenter to work out which is the true one.
Yes, but he said that
angles of a triangle, right? That's the only way you can experiment, really, to find out which is the true geometry, is to measure the angles of triangles.
And he said that this model is possible, and I say that it is impossible. So okay, for him, impossible is possible. Okay.
Yeah, he does have it within reality, right? And he is talking about perpendiculars of a ball. And he's saying that they are straight lines, but just for the making of the map, they're curved. But you have to, they are straight lines.
Yes, but he said that this is these two asymptotes.
Yeah.
He said literally, they in reality, they will never meet. But he is showing here only for demonstration purpose. So this is another just visual trick.
Yeah, but they say that in Euclidean geometry that parallel lines meet at infinity.
Yes, so these lines cannot be enclosed by a ball.
But parallel lines don't meet. So how can they say that they meet at infinity if they don't meet?
Yes, I agree, but
yeah.
but still, he is showing in this picture that these parallel lines, which will never meet, they are meeting, and they are enclosed in point of this intersection. Supposedly, they are enclosed by two balls. And that's why I said that this is impossible. But he says that this is possible.
Yeah, they're meant to be like Euclidean parallel lines. You've got to imagine that those asymptotic parallels are the equivalent to Euclidean parallels.
Yes, I know, but
It's
still,
unimaginable, right? It's that far away from you being able to comprehend it because there's already Euclidean there. You can't replace Euclidean, and you can't think of somewhere different to place this other geometry because it's just not possible. You cannot comprehend it. That's how far away from reality we are here, discussing something that obviously isn't, being claimed imaginary, and people that are obviously mad never actually got there, right? The story of all of this stuff has been developed from nothing. It doesn't actually exist. But this is the introduction. If you're introduced to mathematics and they give you this without a firm understanding of Euclidean, and let's be honest, who has a firm understanding of Euclidean nowadays? Who's given an understanding of Euclidean and where it comes from? The true essentials, going through the definitions and why they literally have to be in the formulation of the logical structure.
I would say that that's the reason why they already got rid of geometry from school.
Yeah.
Because
first off, you get rid of logic, right? You get rid of logic first, because if you understand where logic comes from, then it's much easier to understand geometry through the formulation of the logic. It flows more. So you first off, step one, remove logic from the class, and then step two, get rid of geometry, remove the Euclidean logical structured geometry, and just turn it into circles and squares and triangles, and then place it into trigonometry.
Yes, so they removed that, and now people can listen to that without saying that this guy is mad. Because with knowledge of logic and geometry, all would say that Gauss, this Riemann, and this Hungarian guys, and this presenter, they are all mad. But without knowing geometry and logic, they can take it as serious mathematics. For me, this is just crazy. Just madhouse.
Yeah, this is
already.
It's meant to be further mathematics, but I mean, it's beyond reality. So I suppose technically it is further. It's higher, but it's just gone into the realms of imaginometry, right? It's been taken out of the logical structure.
Yes, a word created from nothing. Yes.
Yeah.
Either you can see it from outside as a map of the three-dimensional non-Euclidean space discovered by Bolyai and Lobachevsky, or you can see it from inside as a non-Euclidean three-dimensional space in which we have an accurate picture of another geometry, perhaps unfamiliar to us, but logically possible, the remarkable world of two-dimensional Euclidean geometry.
Like within that is Euclidean, and they say two-dimensional Euclidean, when really the entire thing is within three-dimensional Euclidean.
Yes, so they are turning 2D Euclidean geometry into this 3D new geometry. So yes, and that's why they require curved lines. And they name it straight lines, but they are curved, and then you can depict 3D geometry, 3D reality within only 2 coordinates, because these coordinates are curved already. For me, this is just a fraud, but okay.
This was my introduction into non-Euclidean geometry, and I'm pretty sure when most people state non-Euclidean, they're not aware of what they're saying. You know, in the lens that these people have gone mad trying to do that, and now there are people that can just sort of take it on as though, you know, other people, there's some shadow giant in the past that sorted this, and it's not needed for today's people to even look at it, because I mean, who does nowadays? What is a mathematician? What would you imagine comes from mathematicians nowadays? Most people are taught that they don't really understand mathematics, and you know, not really for you. I mean, who would use it, and what would you do? You go to university to become a mathematician.
That kind of mathematics, yes, I would say I don't understand.
Yeah.
Because, you know, our imagination works and logic works together within reality, and we are just comparing things to reality. Because in order to imagine something, you have to depict it in especially geometry. You have to imagine that like an image of something. That's why he was presenting these balls, curved lines. So in fact, what they are doing is just redefining already known things. So they are showing curved line, and they say that this is straight line now. In fact, this is what they are doing. So for me, this is that's why I call it a fraud. For me, this is just a fraud. But that's me.
Always worth going back over these things to see. If anybody's out there and they want to go over it, these sort of things, these videos, we go over them quite a lot in the on the level Discord server, because obviously the copyright. So these sort of things, both Bob the Science Guy and the BBC, are known to put copyright strikes out. So we have to be careful with that sort of stuff. But there's some gems hidden within learning, because I mean, most of this stuff nowadays it's what you go over is in your own mind, and you just come to terms, you're trying to work things out for yourself. And these sort of programs, I mean, when we listen to that at first, it's fantastic, because you're still trying to come to comprehend what he's going on about. But once you've actually gone over the triangle axiom and worked all the way through the definitions, and then the axioms, and then the postulates, and you learn the differences between the three, and then you go into going through the propositions, you do really get an understand of how a demonstration works through a logical system. You get to see the building of this logical axiomatic system, and then how that actually gets employed and gets built upon step by step. It's quite good. But if you haven't got that understanding, when you're hearing at the beginning about these 5 postulates and the parallel postulate. It can sound really strange, but it's not. It's really simple once you break it down to the advanced simplicity of it all. The way that what we've learned is to make it as simple as possible, and really it's not as complicated as what a lot of people with these videos like this video make it seem. That's just fantasy. That's people making models. We do have a few videos that are easy to see how this goes over and how people go over this sort of stuff. I remember the hyperbolic geometry and way Penrose was talking about the angels and the demons is that they made the geometry so that they could stand on the outside and look in to see infinity. So infinity is at the boundary of this thing. And I think it's a way for them to imagine themselves as gods, to see the outside limit of infinity. Because obviously it's over there. You're never going to get there. But with this, you can actually stand and see the boundary. Just imagine it is infinity.
But if it is infinity, if you can see boundary of infinity, it means that you are outside of it. It means that you are greater than infinity.
Exactly. It's the monad, isn't it? Like the monad's there at the center. You're looking in at it from the outside. You're placing the monad. It's so obvious, really.
And I would say that they know, these Hungarian guys, they knew that this is madness. So now we have mad mathematics, I would say.
Yeah, internalizing of placing it at the center. It's always about the center. If you have the center, do you leave yourself for this monadic belief system? If you have epoche and have things as they are, then I don't think there's any need to even contemplate imagining any of this stuff.
Especially that they are inconsistent, and just some of these depictions are just magic tricks or visual tricks. So, because in order to explain what's going on within this geometry or imaginometry, he is showing something, but he insists that we have to interpret this image in different way.
Yeah, but not giving you an idea how to do it, right? That's it.
Yes.
That's how the trick's done. It's left up to you to interpret it however you want, and that's then obviously how this is.
As on this picture, we have two curved lines, these asymptotes, and they are, but you have, in order to supposedly understand what he's saying, you have to imagine that these two curved lines are straight. So this is the trick.
Yeah. Yeah, the moment you do imagine, then you're playing the game.
Yeah, but literally, it is impossible to imagine. You cannot imagine that these curved lines are straight. How can you imagine? You have to compare them to real straight line. And you have this straight line on this picture. In the small ball, you have this diameter or whatever, real straight line. So you can compare them. And you can say that they are different. These two lines are curved and this one line is straight. But no. He says they are all straight lines. But for me, this is just madness.
Yeah.
All right. I am off to bed. Good
Okay.
night, all. Thank you very much.
Night. Yeah. Anyone else got anything? It is midnight.
No, good stuff today. I mean, it's like, it sucks having to try to play around someone who's going to use fair use as a weapon and didn't think they're smart about it. But just the way things got to be done sometimes.
It's okay with the BBC thing because you're better off not really seeing it because it's just madness. But like listening to the quotes, going back over the formulation of non-Euclidean, I think it's fantastic. And the people that we talk to that go over non-Euclidean, they're not equipped to even comprehend what it is. Like most people like you talk about think non-Euclidean is the surface of a sphere, but the sphere is Euclidean. And it's hardly surprising when you talk about this, because within that sphere there, the little yellow one, they have triangles having 180 degrees. Yet there's a group of people that say that triangles have more than 180 degrees. Amazing. Within non-Euclidean geometry too. If that isn't contradictory, then I don't know what is. How you can have the inside of a sphere having 180. Also a plane having 180, but the outside of the sphere are having more. What have we got? You don't understand triangles. You get to see this guy in it. Okay, thank you very much for watching. It's Tuesday tomorrow. Don't know whether we'll be out. Might play a video. Might have a video for you. Might come back. Don't know. We'll see how it goes. Watch out for us. We'll probably be back Wednesday, if not tomorrow. Thanks for watching.
You call it a triangle axiom.
I do, yeah.
Thank you, Mike.
Right, so you've managed to confuse a lot of people within that argument. Weird times, buddy. Because like you weren't trying to say that all horizontals are not parallel because you can draw a cross on a piece of paper.
I was temporarily agreeing.
That wasn't the argument.
For fuck's sake.
Because some people have took it as though that is.
I'm sorry. A separate discussion. Happy to talk about that one day. What I originally suggested, and Mike knows this, Mike Jones. We agreed we'd sort of discuss the postulate first. And you call it the triangle last time.
I do, yeah.
I discussed the swimming pool. Thank you, Mike. Question.
Weird times, buddy.
Be quiet. Swimming pool. Thank you, Mike. Question.
You don't understand.
For fuck's sake, I'm sorry. Thank you, Mike.
It's not my problem if you don't want to learn.
Thank you, Mike.
You're just on your own.
Well, that I hold to be a self-evident. You call it the triangle axiom.
I do, yeah. Because it's got just about a triangle, yeah.
The question is, why did include that axiom? You call it the triangle axiom. That postulate.
I do, yeah.
Why did you include that at all? You call it the triangle axiom.
I do, because it sort of shows that triangles have 180 degrees, right? Or some are two right angles.
You know? So you're saying how does it show? Be quiet. Well, yeah, it does. I mean, you can prove that, but why did he include that? You call it the triangle axiom. If you can.
Oh, you can prove it.
Be quiet. If you can prove that triangles have. You call it the triangle. The sum of the angles is two right angles. Why would you need? For fuck's sake. I'm sorry. That's my question. You call it the triangle axiom.
You don't understand.
You call it the triangle axiom.
You don't understand.
I was temporarily agreeing. Be quiet.
It's not my problem if you don't want
just, as I suggested, you just sort of get a horizontal plane. That I hold to be a self-evident truth. You put two crossing lines on them, and by definition, any two lines, straight lines on a horizontal plane, are themselves horizontal. Thank you, Mike. So, that's the problem. You can't. Well, it's not really a problem. Yeah,
it's not a problem because there's only three straight lines. How fucking difficult can it be?
Point again is that you cannot prove it. A lot of people, you call it the triangle centuries, millennia, thought you could prove the fifth postulate. You call it the triangle axiom. The question is, do we need the enclosure axiom? Yeah, not on the globe hypothesis. I received opinions we don't need it because postulate 1 will do the job for you. And look, Bev, I simply wanted to ask you why you think the postulate's there, and you have explained that. And you have explained that. Not on the globe hypothesis. That I hold to be a self-evident truth. I'm sorry. It's not my problem if you don't want to learn. Be quiet. You just on your own. I'll be perfectly honest. I'm sure there are better people back at the other place, the blue place, who can prove this. And we're happy to talk to you.
No logic, no wisdom, no worries.
And you have explained that.
You're just on your own.
You know.
Logic, no answers to questions.
And you have explained that.
You're just on your own.
Right? That I hold to be a self-evident.
It's a self-evident truth of reality that all triangles, in reality, have 180 or the sum of two right angles.
Be quiet. Not on the globe. Well, it's an assumption.
It's not an assumption, is it?
Sorry. For Euclid, it was an assumption because he knew he couldn't prove it. There was a huge debate which went on for centuries. You call it the triangle axiom.
What, that you couldn't prove that triangles have 180
They tried.
degrees?
They thought there was a question: is the fifth postulate? You call it the triangle axiom. Triangle axiom. Is it self-evident or not? A huge debate.
Weird times, Betty.
Thank you, Mike.
Weird times, Betty. You've brought an argument into a group of people that aren't ready for it.
Be quiet. You cannot. Euclidean geometry. You call it the triangle axiom. It does not follow. It doesn't work. Not on the globe. I don't need it as an assumption because we can prove it. You can prove it from the first postulate. For fuck's sake. Horizontal lines can easily not be. You can just, as I suggested, you just sort of get a horizontal plane, right? Thank you, Mike. You put two crossing lines on them, and by definition, any two lines, straight lines on a horizontal plane, are themselves horizontal. For fuck's sake, I'm sorry.
You don't understand.
Well, that I hold to be a self-evident truth. For fuck's sake.
You don't understand.
If you could prove it, it wouldn't be a postulate.
It's not my problem if you don't want to learn. You're just on your own.
You call it the triangle axiom.
I do, yeah, because he's got just about a triangle, yeah.
The question is, why did Euclid include that axiom? You call it the triangle, that postulate or axiom. Why did he include that at all? Thank you, Mike.
Because it sort of shows that triangles have 180 degrees, right? Or the sum of two right angles.
Not on the globe. You're saying, for fuck's sake. How does it show? Well, yeah, it does. I mean, you can prove that, but why did he include that? Be quiet. If you can.
Oh, you can prove it.
You call it the triangle axiom. If you can prove that triangles have the sum of the angles is two right angles, why would you need postulate? That's my question. I will not verbally disagree with it. What goes on in my own head is my own business. I do not believe that. Be quiet.
You don't understand.
You call it the triangle axiom. For fuck's sake, I'm sorry.
It's not my problem if you don't want to learn. You're just on your own.
Yourself, not something to be quiet.
You have a horizontal plane, and any straight line not on the globe must itself be horizontal. That I hold to be a self-evident truth. Yeah, not on the globe hypothesis. I was temporarily agreeing.
Right, so you've managed to confuse a lot of people within that argument.
I was temporarily agreeing.
Because you weren't trying to say that all horizontals are not parallel because you can draw
not on the
cross on a piece of paper, are you?
Thank you, Mike.
That wasn't the argument.
Not on the globe.
Because some people have took it as though that is.
For fuck's sake. Separate discussion. Happy to talk about that one day.
Yourself, not something to be quiet.
Point again is that you cannot prove it. A lot of people, you call it the triangle axis. Centuries, millennia, thought you could prove the fifth postulate. You call it the triangle axis from the preceding thought. Be quiet. I was temporarily agreeing. But not on the globe pipe. You call it the triangle axis. But not on the globe pipe. It's not my problem if you don't want to learn. Be quiet. That I hold to be a self-evident truth. Oh, for fuck's sake, I'm sorry. No reason, no logic, no wisdom, no worries. And you have explained that. You're just on your own. But not on the globe, no. No reason, no logic, no answers to question. And you have explained that. You're just on your own.
Betty, do you believe the water surface is a horizontal plane of reference?
It's a horizontal plane, possibly, but not on the globe. Let's assume.
Thank you.
The surface of either swimming pool is a horizontal plane. Establishes a horizontal plane of reference, right? Let's assume.
Thank you.
The surface of either swimming pool establishes a horizontal plane of reference, right? It's not really a problem. Yeah,
it's not a problem because there's only 3 straight lines. How fucking difficult can it be?